тебя полишнее.
All right, everyone, we're going to get started.
I'm sorry, can we wait? We're having a problem with the stream.
Okay, we will wait for the stream.
So we were ready for waiting more.
Yes, please let us know when you're ready.
What room is this? Is this the method room?
This is 104, which is
That's the function
the
room.
function room.
Ethan, did your room start yet? Can you ask them to please stop? We're having an issue with the stream.
Really sorry, I want to make sure my stream is connected on my.
Yes, I'll take a sec. On the Dagger Slack. Yep.
Which track is this room?
This is the Dagger BOF. Dagger Birds of a Feather.
Okay, yeah. I got that this was the method room, but I think that I was wrong.
Oh, gotcha. Okay. Is it?
Testing, testing.
The method track.
And then, let me, I guess I should also share screen.
Wearing a blue t-shirt?
Yes, yeah. They were here for a computational chemistry conference.
One second. Sure, no problem.
Actually, I think the people I was talking to from the computational chemistry conference, they were actually in the middle of kind of ranting about the issues getting started with HPC, actually, which I thought was hilarious. One of them is basically managing the cluster itself because no one has helped manage it for them. The other person is, on the other hand,
Thank you.
managed experience.
All right, we're going to get started. Welcome to the Dagger Birds of a Feather. Thank you all for being here, and if you're on Zoom, thank you for being here as well. I posted in the Dagger channel the Zoom link, just a point. I'm not looking at Zoom right now, but if you are on Zoom, please just make sure to keep your microphone muted unless you have a question, and we may repeat just so that the stream can hear it. So just a quick introduction to who's here. So myself, Julian Samru, I work at MIT's Julia Lab as an RSE.
I'm also here. I'm Felipe. I'm a research consultant at MIT, also at Julia Lab.
And then I'm not sure if she's here on the stream, but Rabab is a postdoctoral fellow at MIT, and she has been a very close collaborator of ours. She wasn't able to make it to JuliaCon this year. Just as a quick overview of what we're going to be going through today, so we're going to give a quick overview of some of the stuff that we've been doing with Dagger. We're going to go through a few polls and some discussion points kind of relating to like what people want from Dagger, what they've been doing with Dagger, and then we'll have time for really just open discussion, kind of like a semi-panel, send the mic around the room and just talk about stuff sort of thing. So just checking real quick, Rabab, are you on the Zoom? No problem. So just to kind of start off, so Dagger is an asynchronous task runtime, many task runtime, and there are many like it. For example, people have probably heard of Cocos, Legion, OpenMP. They all kind of, we all kind of relate to them in different ways. You know, there's also, Alan will tell us all about StarPU if we ask him, as one of those parallel runtimes. What?
StarP, no.
Oh, yeah?
StarP.
Oh, it's StarP. I see. That's right. My apologies. There's also runtimes like Parsec. Many of these have been involved in things like Gordon Bell submissions, and I believe have won Gordon Bell a number of times. That is also something we're aiming for eventually. But anyway, Dagger is a Julia native parallel task runtime, and it has a variety of components that does quite a lot of things. If you saw our talk 2 days ago, you know about some of these things. So why don't you go ahead and take this?
So as the goal for any runtime, basically our job is to make things easier or to provide parallelism easier. So we needed to have a consolidated API to do in-place linear algebra or any in-place operation that needs data dependencies, so that the user may know what will be done in the data they are providing to a function or a task, and we take care of the rest. We do the synchronization, we do the scheduling based on that, and the mapping based on the DAG. So what you're seeing on the screen right now is a testament to the productivity that Dagger may bring. This is a Koleski factorization. It's 21 lines long, and that's it. 22 lines long.
There's some white space.
There's some white space, come on. But,
Okay.
18, right? Whatever. Yeah. But anyways, the point is, it's short. It's short. And it, as I've mentioned, is a testament to the goal of Dagger, which is to provide not only performance, but to provide productivity. As Alan has mentioned a lot in the meetings we had, and here also, the goal of HPC shouldn't just be performance, but also usability and productivity. So this is one example. So that, what you saw, was the testament of productivity, the number of LOCs. This is the basically malleability and the applications you can do with Dagger. So Rabab right now is working on multiple precision or mixed precision, what you may call, and tile-based algorithms. I myself am working in these things also. Dagger provides a good test bed for doing small changes to code and providing a lot of usability. As if you came to the Dagger talk, and if you didn't know, I'll explain a little bit. You can just put a line of code and use MPI if you don't want to use TCP. And it provides also for the expandability of not using MPI, and eventually we can implement UCX if you want. So there's a bunch of algorithms that are portable, that are performant, as you can see in the graph there.
So I just want to make a point for everybody that what you see on the screen right now, this style of writing algorithms, is reasonably new to Dagger. It's come about in the last, I think, 2 years. 1 year. And so this is what we call data depths. This is something that we are pushing forward with very hard at Dagger. This is basically a unified way and a straightforward, simple way to implement highly parallel algorithms in Dagger. Now, we have implemented a few of these in Dagger. This is actually taken from the Dagger source. This is our Cholesky algorithm. We have a few others for matrix multiply, array allocation, things like that. And as I mentioned at our talk 2 days ago, we are looking for people to help implement more algorithms using this interface. And, you know, just as some motivation, you know, if you need it, this algorithm supports multi-threading, distributed, and all 5 GPU vendors currently supported, or GPU programming interfaces supported by Julia right now. And so it's extremely powerful, as Felipe was saying, and so, you know, this is, you're gonna see a lot more of this going forward. Yes, question?
So, I've been
Oh,
thinking-
we got a mic. Thank you.
You can also repeat the question.
Yeah, that's true.
It's easier. It's easier
But for the back.
to have the mic. Yeah.
I've been thinking about this because currently we do not have a fully consolidated way of doing parallelism across the ecosystem.
Right.
And writing algorithms is hard, and you don't write them in too many ways. Also, Dagger is not the most lightweight dependency in the ecosystem, for which there are very good reasons, and it's gotten much lighter, but still less. And it will probably still get lighter, but there may be a limit. Can we have, this is essentially a kind of language, right, the spawn. Can we have this as a lightweight package for which Dagger can be a backend? So people can depend on something very lightweight and put these macros in their algorithm, which can then run without any special, which will just run like normal Julia code with very little overhead, but has something that Dagger and possibly others can hook into, so we can really make people write algorithms in a way that can make use of it without depending on it.
Right, yeah, that's a great question. And I know we actually spoke about this at, I think, the last JuliaCon. And so this definitely does not have to be specific to Dagger. We could pull this API out and pull it into its own lighter weight package. There are some complications, not complications, but some of the heaviness of this API is not just due to Dagger itself. It's also due to the fact that, let me see if we actually have it in here. There is a lot of what's called aliasing analysis that goes on behind the scenes in data depths. So for example, when you read or write to a given argument, you need to actually, the data depths needs to look at that argument, recurse through the argument to construct what we call aliasing info, to basically determine, like, you know, how does it overlap with other arguments, and thus how do we safely parallelize this algorithm. That is still somewhat heavyweight. It's still a little bit expensive, and it's also currently pretty tightly integrated into Dagger through our chunk objects, through dtasks. There's a lot of things that are interwoven. Now, that's not to say that I wouldn't be interested in seeing an attempt to pull this out, and if we could do that in a reasonable way while still obviously having Dagger support for this, you know, work exactly the same as you see it on the screen today, I'd be open to that. But I think we would need a collaborator who's interested to actually work on that. Okay, awesome. So I've got a volunteer then. Yeah, but great point. Question?
Maybe just trying to understand the intended scope. Is the idea that your resources are fixed over time and not changing, or is the idea that as the problems get bigger, you'll ask for resources, get them, and give them back when you don't need them?
You're talking about dynamically adding resources like workers and stuff like that. The Dagger supports this. We haven't made a lot of progress on this recently, but the interfaces for this exist within Dagger. It's possible to today, while a computation is ongoing, call, say, distributed add procs, call dagger.addprocs to tell Dagger about these new workers, and Dagger will start integrating them into running computations, into tasks that have not yet started.
But if you're on like a cluster, can you interface with something like Slurm to like request resources, and when you get them, like?
Not yet. That's
within the scope of what you want.
right. That's mostly something that we just need an interested collaborator to help out with, and we would be happy to provide guidance on that. But yes, that's very interesting to us.
Hi,
I just want to comment something. I stopped using Dagger a little bit ago because I have other projects, but when I did it back, you helped me a lot. There was this very interesting application using Apple Silicon because you can have the same memory mapped to the GPU and the CPU, so you can execute the algorithm without the how can I say, the time it takes to copy the things, the overhead.
Yep.
Does it get any better? We will mention something about it. When you use these spawn, how can I make it work on those platforms so that we do not need to copy things between the GPU and the CPU? Is that something easier to do, or I need to do it manually?
Not yet. Our memory space model, which is what this is also based on, doesn't yet have a great, well, actually, it may be possible. We would have to take a look at the memory space model that I just mentioned. In theory, it should allow, for example, metal processors to read and write simultaneously to data in both spaces. The question would be, can you represent a piece of data as living in both spaces? Not today, presumably, but we can take a look at that. And again, if you're interested in working on that,
Yeah.
We can provide guidance and kind of figure out what that looks
Perfect,
like.
thanks.
Yeah, we messed a little bit with the memory space model for MPI, and that kind of helped us understand better how can we do that, like how we could do that. So there's a path kind of open already, and we can easily traverse it together.
Sorry. So when you run this, essentially the whole program runs through immediately, right? Because all the spawns basically return something like a very powerful sort of future. So and while this program runs, which it doesn't really do yet, it builds the computational graph. Does it build the whole graph at once? Because that could get very huge in some places, or will it basically stop in some places that still wait for an input and basically build parts of the graph dynamically as all dependencies come in? So is it a full upfront or lazy construction of the computational graph?
Yeah. At this point, it builds the whole graph basically. However, there's like work to be done to basically split the graphs or distribute the DAG basically building. We thought of doing that first with MPI. Ian, which I think is in the Zoom right now, probably, is working on that with the GSoC, like the Google Server of Code. So it's a project already. And that was one of the first things we thought when we started using data depth. So if we do this ahead of time, we will run out of memory or space, or it gets too big, the analysis gets too heavy. So it's work being done. It's work in progress as we speak.
And there's also some ongoing work to improve the scheduler, to use a jump-based scheduler for like more optimal scheduling. That one also works on sub-DAGs at a time. It finds essentially DAGs that it has enough information for to fully consider all at once. We could reasonably easily do that a little bit earlier in the process of actually running through this program and pause at a given DAG or at spawn call and start doing the analysis there. It would be reasonable. We have the microphone up here. Yep, go ahead.
Just to complement my previous question, so you understand my use case, which is very, very interesting. We have this satellite simulator, and our bottleneck is a part we compute the Earth albedo. We have the sunlight hitting the Earth and then sent back to the solar sensors, which cause some perturbations. So we have this huge matrix. If for each point in latitude and longitude, I have to compute something, which is very simple, but it's a lot of computations. In the GPU, it's way faster, but the time to copy every single step between the GPU and the CPU makes it just unfeasible. So if I have this single map between the GPU and CPU and can dispatch to the CPU, to the GPU while I'm computing other things, and then have it ready by the end of the step, it would be way faster. This is our bottleneck. That's why I will pursue this. If you can help me, maybe I can provide something to the Dagger.
Yeah, I would say it's completely feasible, right?
Yeah, and also for the AMD APUs.
Yeah.
It's the same thing.
Yeah.
And NVIDIA too actually has.
Yeah, this has become a trend, I think, in like silicon basically, because NVIDIA has the GA superchip right now. It will be building superchips in the future, like forever. AMD has its APUs. As you mentioned, Metal. So it's a good thing to have the technology in Dagger to support these things. So yeah, we would love to have everything that has a use case for Dagger is great for us, because then we can basically have something to break it, and then we can fix it.
Right. Thanks. Thank you.
You had another thing right here? Oh, you had another? Oh, yeah.
Okay.
So we have a lot of for loops in here, and then in the for loops we have Dagger spawns. Is there something, or do you plan something to have like more like a map primitive, so that you can, basically have more, keep the semantic information that you're going over a collection here for longer, and then you could also say, well, if no element of that collection is there yet, then I don't have to build the subgraph yet, because I'm still waiting for any of it to come in, so I can't even do anything on it yet.
Yes. So basically just knowing that there's more to do, essentially. Like knowledge that you're not done filling the graph, which allows you to determine whether you should continue slurping up tasks or whether you should pause and execute. Yeah, that's a great point. I've thought about that a lot. I need to think about it more. There are a lot of considerations on what that even should look like. Yeah, exactly. And I think we need to work through that a little bit more. We can experiment with that and see what happens if we just implement, pausing at Dagger at spawn and see what happens with that. I think once the new scheduler framework is implemented, that will be an excellent time to start exploring this more. So, and we'll try to keep everyone updated on that progress.
I just had a quick question on scope and size for when you would switch to use something like Dagger. Like what size data set or what size of complexity of the problem where the trade-off becomes worth it?
I would say that, as a good example also, this Koleski is, I wouldn't say better, but it's more performant than OpenBlast for matrices that are bigger than 1,000 by 1,000.
So at 1,000 by 1,000, you see a performance gain that beats traditional
At
approaches.
least for this algorithm, yes.
On multi-threading,
Yeah.
which is
Yeah.
what OpenBlast should be better at.
Right.
Yeah.
And so this Dagger is good for, let's say we don't necessarily have GPUs, we're cloud-based, we're all on EC2 instances, and we're kind of doing the normal Julia multi-threading approaches, just kind of faking it ourselves to build stuff. So I could use this and then wrap up what I'm doing and basically pump the same things I'm building through Dagger, right? My same algorithms or my same matrices, right? So if I'm doing some kind of optimization or simulation, I could still do the same thing and spawn it out with Dagger.
Yeah, sure.
Okay.
You mentioned the cloud. One thing that makes us stand out a little is that distributed next, which is set by a preference in Dagger, uses TCP. So it plays out with the cloud. The other runtimes, not so much. So
if I do an EC2 instance where I have GPUs on my EC2 instance, then I can absolutely use this.
yes.
Perfect.
And maybe if file I/O is a significant cost, is there some way that like it knows that this call is going to be really slow because it's going to involve a read from disk, and this call is going to be really fast because it's just computing stuff that's already allocated, or would the user have to somehow signal that?
Yeah, generally, if you're doing I/O in a task, You're kind of talking about like critical path and considering that a given task may take longer, and so you want to start making better decisions based on how long that task takes.
Well, I think, for example, if I were hand coding everything, I might say, read in the first 10 files, start processing one, while you're processing one, read in file 11, right? And just kind of like try
Right.
to keep it
Yeah.
so that when it's ready to do the work, it'll have this stuff read in from disk, and maybe I even know like something about how the files are on my network, and therefore I could just read local things and cache it. I mean, like, I don't know how clever you could be, infinitely clever, right?
Yeah, that's a great point. So Dagger has a file structure that you can construct with basically a path and then a serializer and deserializer function. So it lets you basically say, at this path, there is some arbitrary data, here's how you load it. And you can pass that in as an argument to a Dagger, to like a Dagger task. What will happen is that on demand, when Dagger is ready to actually start executing that task, it will load in that data, and seamlessly in the background, Dagger's memory management library mempool will keep that in memory for as long as it makes sense, as long as there is demand for it and there's not too much memory pressure, and if necessary, it will allow it to be paged back out to disk. So Dagger does have some smarts there. We need a little bit more work. You made the point about like local versus remote. If the file is both locally accessible but also remotely accessible, we don't yet have a way to express that they're the same object, they're the same file, but that's something that I want to add. If you're interested in taking a look at this, again, please reach out and we can collaborate on building that.
Yeah, so I'm glad you brought that up, because this is exactly sort of the same problem I have. This was a talk that I'd invited you to, Julian, with the range extractor stuff, which I probably ran a little over time. But the whole idea there, right, is that there are certain files which may be needed for multiple task streams, if you will, and there are certain files which you won't. And so I can classify those on my end, but I would really love to be able to use Dagger's memory management and queuing and all of that stuff to be able to do that. But one of the things there, right, is that when you're using what I call a chunk and range extractor, that's not necessarily a file. That could be just an HTTP request that gets sent, and that HTTP request contains some byte range to a larger file, which you then retrieve, and maybe you cache that, maybe you say, hey, I don't have disk space, don't cache anything, please. Right? So that's also sort of a part of that story that I was wondering if it makes sense to do in Dagger, not really, could do, could not do.
Yeah, I mean, that kind of is in the realm of like fancier I/O support and fancier knowledge about, I mean, things like aliasing for I/O, which the local versus remote networking is kind of an instance of that. And then in this case, looking at a chunk of a larger object over HTTP, whatever the network protocol is also an instance of that. So I think we don't have support for that yet. I think we should have support for that, but again, we would need to take a look at your code again and kind of work through like, what would that look like for you? What would that look like for the local versus remote problem, which is actually quite common. We see that a lot, and try to build something combined. We can switch the mic back and forth and whatever.
Thanks.
Works.
Yeah, I just wanted to say, if you guys are all around during the hackathon, maybe we could carve out like 20 minutes, half an hour, look over things and start from there.
Yep. We'll both be there.
Yep. So for my collaboration, we're now running regularly in parallel with Julia about like, I don't know, 50, 60, 70 terabytes of data, soon 100. Currently doing this with parallel processing tools and a very primitive handwritten data dApps. Because what we found out and what we need in Dagger is what really matters is timeouts, retries, and allowing for failure. Because weird stuff just happens sometimes. Right. You use algorithms written by other people. On that specific input, the algorithm might get stuck, or something is on that node that just makes it take unreasonably long, and you just wanted to time out, kill it, and try again, possibly on a different node. And sometimes there is just some file where, despite all your optimization and your algorithm, it's just, or some part of the input, it just doesn't work. You have to admit failure, you want to log that failure, you want to document the failure, but no number of retries will make it work because you have to look again by hand at the data and fix your analysis approach. So how can we have this combination of timeout, retry, and letting failure happen, maybe for a user-selected set of exceptions or so? Is there a path?
It depends on the API. There is a level of fault tolerance built in Dagger. It is not well tested because it is quite fickle. I don't know if that's the right word for it, but this general idea of like supervision, fault tolerance, tolerance for failure, restarts, all that is something that I want to build out. I realize the need for this, especially when we're building out streaming support, because those are long-running tasks that presumably should run forever. I mean, if it's in a production system, it better keep running. It better not fall down. And if it does, it better get right back up. There are a lot of levels at which you can build in fault tolerance. It is tricky. And it is tricky to consider what a good API would be for this as well. And like, do we need supervisor tasks? Do we build this logic directly into Dagger, which I'm not 100% sure about. You know, I don't like the proliferation of too many options that are kind of like use case specific and all that. I'd rather have supervisory tasks or whatever. But this is something that we really would need to kind of talk through and see what makes sense.
Yeah, so the backend implementation is of course far from trivial, but like from a user point of view, when I do this spawn, I know what I'm going to run there, so I can judge how long this should take, so I can set a timeout at 4 times the time. I also know which exceptions mean I want to retry it, which exceptions mean I have to admit failure. So I have a feeling that that is something that has to go with the spawn, because there really only the user knows, and it can be very different for different things they spawn.
Right. So one thought I had is presumably we could allow, so you spawning the task, you also have control over the function that you're calling. So one thought is that what you may want to do is encode that into the function that you call a wrapper function that will call your actual payload function with the data, provide some additional arguments that say, okay, timeout after X amount of time, do certain behaviors like mark this task as dead, start a new one. We could provide some primitives, some built-ins in Dagger to allow you to ask the scheduler to do certain actions for you, so that you can fully program out whatever logic you want for that. We also have, I'm not sure if you were at the cancellation talk yesterday.
But that is a big thing, of course.
Yeah.
You reliably cancel something.
Right, cancellation is huge, and it's...
Can't fully do, but from what I understand, it's coming.
Yeah, right. In Julia, we can't, it's not pervasive. In Dagger, we have a cancellation system built in, and what I was going to say is you can actually leverage Dagger.cancel and the cancel token, which is available to every single task and is task local. If, for example, you need to propagate cancellation information, if your wrapper, for example, wants to notify that token to tell code that it is calling, hi, you need to just stop, you're done. That infrastructure already exists, and you would be able to leverage that for more fancy kind of approaches. Again, all of this ends up being application specific, use case specific, so we should take a look at like what your common failure modes are, what your code kind of looks like, and the best way to approach this.
Yes, so this is kind of like cooperative cancellation, right?
Yes,
the running
absolutely.
code has to look in the token. But sometimes you just have to call some algorithm from some package, and they run some fitter loop. They are not looking at the token. So what we do at the moment, if all else fails, we kill the worker. And then the next step will be to write a wrapper around the worker that within that Slurm slot, not giving up the Slurm slot, just restarts it. Kind of like Erlang. If everything else fails, you just kill it. Like
right.
as a last resort.
you can do that, and Dagger's fault tolerance mechanisms will kick in that case. I'm generally not a fan of having to do destructive things like that, but there are many cases where that is the only thing you can do. And again, if you watch my talk, I make the point very clearly, arbitrary code is not interruptible without being built specifically for interrupting and cancellation. And so again, the forceful thing you can do is pull the power plug, kill the worker. And Dagger, its fault tolerance, while it's not yet up to snuff for production use cases, we very much want it to be, and there's no reason it can't be. We have all of the logic in there for it.
Not an easy thing to build.
Right, it is not an easy thing to build. And so we would love, if you're interested in taking a look at that with us, we can get that back up to spec, get all of the CI working cleanly, test a bunch of use cases. I'm very interested in this. So yeah, let's speak about it offline. If there are no other questions, we will continue onwards. But this discussion is great. Please feel free at any time. If you have any questions, any discussion points, just bring them up. So let's just do a quick poll. So raise of hands, who actively uses Dagger for work? Okay, I got one. I mean, we've got to raise our hands, obviously. Okay, and this is fine. This is kind of what I expected. We're still early stages with Dagger, and we are working towards next year having there be a lot more hands up. So again, and this is why we're, part of the reason we're very open to discussion, we want to see what is blocking people from being able to use Dagger. Sana, you raised your hand, so I'm gonna single you out. What actually worked well for you? And microphone's up here. If you don't mind answering, of course.
Yeah, so writing my algorithm in Dagger was very easy, but yeah, it was very easy. It was easily being implemented on different GPUs, CPUs, and it's also easy for user to use my code. But the problem is the speed. I mean, I had the speed problem all the time.
So that leads us to our next poll, raise of hands, who tried Dagger and failed? 1, 2, 3, 4, 5. I've also had problems with Dagger. Okay, yeah, a lot more hands raised, and that's fine. So why did Dagger fail for you? Well, Sana, you said that speed, bad performance, was one of those. Chris, yeah?
Yeah, so I think one of the things that I would kind of throw out there as like a, philosophical thing to kind of consider with the going forward of Dagger is, I build a lot of package ecosystems, and there's certain things that I'll ask about performance, like, oh, have you thought about integrating with React and yada yada yada, like and those are questions and discussions to be had. But I think the higher level philosophical thing with Dagger is it possible for Dagger to be able to build the right APIs so that way you can give things about you can give things about the information about the implementation that is what you want to do in terms of the organization, separate from the underlying implementation for execution. And what I mean by that is, there are a lot of things that I can say, oh, you know what, a good way to think about this project is I want to do these different tasks, and I want to do something here, I want to do something here. But if I right now want to commit to Dagger, then I'm saying, oh, I'm committing my package to be doing all of these through distributed tasks. And for 99% of users, that is the wrong thing to do for performance, because, oh, they don't need a task, they don't need the mutation, and they're not using distributed, right? And so, but in terms of what I'm thinking though, is the task flow, it can be good, right? So could I set up my package to be able to say, this is how it should be structured, but in most cases, delete the task, make them no ops because it's just for my organization, right? Just inline code when you can. But you know what? If they actually have the right computer, use multi-threading. And if they're in the right environment, now automatically distribute this, right? I think that's the key, because I want to be able to build my package so that way it's Dagger compatible, but I don't want my package to be a distributed package for HPC people. And there's a big difference between the two.
Right. Yeah, go ahead.
it goes to your point, right? I don't know if you were here or not, but I will repeat what he said. He was looking at, oh, it's not on the screen, but he was looking at data depths specifically, not only like this modularization in general for everything Dagger, but he was specifically interested in stripping data depths out of Dagger and turning this into a standalone thing that may integrate easily with Dagger because it was born here. And that idea requires two things that are not impossible. It requires effort from our side and requires heavy feedback from the user because it basically overhauls the whole architecture we have right now, which is monolithic, as you already mentioned. So it's not impossible. It's something that if you guarantee us that you use it or you have interested in it, we can do it. It's not impossible. It's just a matter of discussing and being an ongoing effort between us and the users, or you specifically.
Right. And also, I mean, this point is also part of the reason why I tend to drive people more towards the application-specific APIs, like the D-array, D-tables maybe not so much, but data depths also being one of those where it's less about the tasks and it's more about what is the computation I'm actually trying to do. Let me just express the computation in the most succinct, straightforward, most Julian way, not to use my own name, but in the Julia sense. Like, what is the most natural way to express my problem cleanly? At the same time, not making assumptions that, oh, well, now for every single task, it's going to be distributed. It's going to do whatever, and that's not actually what I want because that's not the performant, optimal thing to do. We're very aware of this. That is why we try to separate, like, the API, how you express the problem, from, like, guarantees and decision-making, where you express your problem and then we try to make the best decision making given that this is how you've expressed your problem and this is the hardware available. And this is our knowledge of the problem from what you've given us from over time, what Dagger has learned as it executes code. Does it always do well at this? No. And that is something like with the optimizing scheduler, we're looking at improving. But if you find a case where Dagger makes a bad decision and it really was clear that Dagger could have made a better decision, please reach out. If there's a case where, hi, I want to express my problem as this either overly coarse-grained or overly fine-grained approach because that just works out better for me in my library, but I don't necessarily want that many tasks or I want these tasks broken out into pieces, that's also something we're interested in working on. So again, if you run into a case like that, we can take a look at that. We can implement some optimizations. Dagger is very flexible. We can do quite a lot with what you give us. Just some of those things just aren't yet implemented, but we just need to know that there's interest. So.
I just wanted to read. I think you were out of the room when I said it, but it was basically that if we had like a lightweight package that does not pull in dependencies like Dagger, that allows us to annotate the structure of a computation. Yeah. Also that we can monitor, that packages can hook into this, oh, I want to monitor this computation, it's long running, like progress information, like serial versus parallel. If we can annotate code like that without having a heavy dependency, and then say, oh, now I'm a big system. I use Dagger as the back end, or I use something else as a back end. That would be awesome if we could come up with really a standard for this, so people don't have to rewrite the algorithm for 3 different parallel backends.
Yeah, and it's lightweight and zero-cost abstraction, right? So you should be able to say, you know, very low dependency.
Yeah. Running locally, you should have 0 overhead.
Exactly.
Right. Almost.
Yeah. So this may be slightly off topic, but one thing that this sort of brought up in my mind was there's this package in Python called Coiled, which you've probably heard of, which basically lets you spawn out AWS jobs. Okay. And I'm wondering whether, with all of this, like once you have this sort of spread out through the ecosystem where packages have these annotations saying, hey, this is how you should run my code, I'm wondering whether this is actually something that Dagger could do better at some point than what currently exists in Python world and other places.
You're saying specifically in the case of like, here's a bunch of jobs, let's just farm it out to say AWS or Slurm or something
Exactly,
like that.
or like JuliaHub.jl or whatever, right?
Yeah, I mean, that's a good point. I mean, I think kind of among the three of you actually right now, there's kind of this aspect of like, what if we keep the API? What if we keep the general ability to like reason about memory spaces and stuff like that, because that's key to the API, but let's take out the scheduler, let's take out some of the extra stuff and have that back end be replaceable. It's a big ask, but it's also potentially big reward. And especially if we can do that, that gives a lot of opportunity for both lighter weight, inclusion into libraries that otherwise wouldn't include Dagger, and also allows more experimentation with like how useful is a task API and an array API built on top of that, a table API built on top, the data depths API. Like, can we still move, easier parallel programming forward by making the Dagger backend optional? And that's worth really thinking through, but it would be some work.
And I think as one example, the linear solve package, right, Chris? It's divided basically. So if you're like running MKL, it will load the MKL dependency. That makes it more lightweight. I think that's where you like get the idea, right?
Yeah, quite a bit, yeah.
I thought so.
Yeah, this is, the more I think about this, the more naive this kind of sounds, but I was originally wondering, what if the alternative to that is that if, Dagger sees that that we're operating only on one thread, we're operating without any distributed kind of resources, then basically just order everything as if it was just vanilla Julia. But the more I think about it, there's going to be overhead just in doing that. So,
well, I mean, you would hope that as Dagger evolves and gets better, that's essentially the performance you tend towards, is as if there was no extra overhead and you just were expressing your problem and it was run sequentially, or maybe just multi-threaded or something like that, and no additional distributed stuff is going on. And that's what we're working towards. And Dagger is also a pretty old library. I picked up maintenance years ago, but it had years of development going on for a while before that. So as we go through, I'm also removing and adapting certain existing ideas that had a lot of overhead but didn't really matter for prior use cases, so that we can cut down this overhead, and to the point where if you're just running multi-threaded, you don't see distributed calls, you don't see any queries about GPUs, you don't see, well, that doesn't really happen, but especially distributed is one of those heavyweight dependencies that you really don't want to have to call into at all if you can avoid it. And we are working towards that. And the latest PR to Dagger actually does a lot of work there, but there's still much more work to be done.
How much have you considered some of the other use cases that are not necessarily about performance, but more about logging, right? So I don't know how much visibility you've had into some of the other use cases that specifically that Pumas has had with Dagger. So for example, one of the ways that Pumas used it, and I don't think it's still in play, right? But it was something that was actually heavily looked into. For example, was for provenance tracking, right? So provenance tracking is something where there's an FDA requirement where you could basically just say, I did this with my data, I did this with my data, I did this with my data, and the Dagger system actually seemed to be a pretty interesting kind of notion with that, because you basically have all of your inputs are tracked and all of your outputs are tracked, and then because you want to be able to say, this is exactly the function that was ran, this is the data that went in, this is the data that went out, and I want to store this, I want to log this, and I want to then be able to give you a report that gives you an interaction graph of everything that was ran, and be able to save this. In a lot of regulatory cases, now I'm kind of changing the different regulatory cases I'm looking at, but for automotive, for aerospace, and all these things, people are looking for a lot of provenance tracking systems, and it seems like, while you're really thinking about Dagger as like, oh, so this can take your computation and distribute it, another potential use case is if it had the right logging information and the right file system integration and such, it could actually be a really good tool for these kinds of aspects. So I wonder if you consider these kinds of use cases and the communities being built around those kinds of tools as well.
Sure, and I just want to say, I know we have another question, but we're about out of time. We're happy to take more questions after the BOF. I just want to say dagger.enable logging, and you get a lot of that information. You get all the argument information, all the tasks launched since you started enable logging. We need to work on performance of that. We need to work on the storage size of that and ability to say write out to a file periodically, whatever, but the logic is all implemented mainly for debugging and visualization purposes. You could very easily do that. We could take a look at that and optimizing that if that's your use case, because we have logging and introspection code at nearly every opportunity for the obvious purpose of debugging. So yeah, we should take a look into that more. But we're out of time. I don't know if we have something after this. I don't want to interrupt that. So thank you all for being here. This was a great session, and we're really interested to hear more about what you're working on, where Dagger has worked, where Dagger hasn't worked, and what you need from Dagger. So thank you, and I'd like to give a round of applause to all of you.
Basically the same questions yesterday.
Yeah.
Like, is Dagger more?
So do you consider this production ready, production safe?
No.
No.
No, I would not make that assumption. However, we need mostly more testing. There have been cases where bugs that we thought were squashed were not squashed, and I
Testing.
Hey everyone, welcome to the Machine Learning Mini Symposium. So we'll start off with pretty much an hour of reactant. So Billy will start with reactant. I will do a Lux demo for reactant. So William is an assistant professor at UIUC. He received his PhD at MIT in computer science. He is well known in the Julia community for his enzyme.jl project, which basically autodiffs through LLVM code. And he also, apart from that, has worked on a lot of C++ side, polygeist, Tapper, right?
Taper, yeah.
Yeah, so a lot of this cool stuff, which he's also going to talk about today in his new project called Reactant. So.
Yeah. Thanks, everybody. This is actually my very first JuliaCon, so I'm very excited to be here. So to start with, like Avik said, I'm going to be telling you about a cool project that we started recently called Reactant. And there are so many people who have worked on various pieces of it that I couldn't find the pictures of everybody's faces offhand, so I at least have all of their wonderful names up here on the board. To sort of start this off, something that I, as a computer scientist, and in particular I as a compiler person, really would like to get fixed is that, usually when you go ahead and write code, the code that you write often has a significant mismatch between, how you want to write it and how you want to go ahead and execute it. So here I have a fairly simple Julia, algebra expression where we have, some matrix x, we square it, we add it with the transpose of x squared. So let's go ahead and see what happens when we actually want to go ahead and run it. It turns out that under the hood, Julia does a lot of things. So the first thing is we have that first x squared, and Julia will allocate a new array for the result of x squared. And of course, inside of that, it'll do a mapmul. Then, of course, we have our second x squared over there, and it'll once again allocate now a second array, and once again do another mapmul. Fortunately, Julia is very nice, and the transpose for us doesn't allocate now a third array, just does it inside of types, which is fantastic. But we're not done with our allocations yet. We have one more allocation. When we add up these two arrays together, we're going to allocate yet another array, and then we're going to actually do the add inside of it. We can summarize this as following. We have 3 different array allocations, 2 mapmuls, and 1 add. So that's cool. That's probably how I'd want to write it. It's how it appears maybe in like some physics equation or whatever else. But that's a lot of allocations, possibly mapmuls, and that extra add there. Anyone have any ideas how we could possibly speed this up? Because I'd like to speed this up at least.
Add a dot at least between a plus equals dot so that you do the addition in place, which is probably going to throw away, so you save 1 allocation.
Yeah, do an addition in place plus equals would save 1 allocation. Anything else that I can do?
Reuse the same x.
Yeah, reuse that same x squared so we don't do it twice. Any other sort of funky things? Not a fan? Well, fortunately, there's a whole sort of diversity of things that we can do. So let's talk about that, try to reuse the initial allocation. So one thing that we might be able to go ahead and do is transpose x squared, if we assume it has the nice properties that we want to assume, is just the same as calling x squared again. So let's just go ahead and say 2 times x squared here. We're saving it. We dive into it a little bit more, and now there's 2 allocations. So we have the x squared allocation, but we still have 1 allocation for that multiply by 2 to put it inside of there. We've reduced the number of mapmuls, though, so mapmuls are expensive. We really want to get rid of that. We no longer have that add, but we now have this mul here. So that's 1 allocation at least a little bit better. Any other ideas for things that we can do? So I don't fault anyone for not knowing this, but if you look inside the linear algebra library, inside of Julia, or in particular, if you spent too much time, like me at one point, staring at the insides of blahs, it turns out that the multiply utility itself is slightly more general than just like A times B. It turns out that the actual runtime call is saying that the output matrix C equals the old output matrix C times some number plus the mapmul times another number. So in fact, inside of that mapmul, whereas it's normally by default set to multiply x times the number 1 and then plus 0 of the old output here, we could do this without that extra allocation, without that extra 2 even, all inside of 1 mapmul utility by just cleverly shoving that extra square inside of there. So now we have a much nicer version, 1 allocation, 1 mapmul, no extra stuff inside of it. Beautiful. No one wants to write that. I mean, some vague amounts of performance engineers. can write that, and sometimes you have to write that. But my overall question here is, can we build something that enables us to not have to write this? Especially because as soon as I want to go to, say, a different device, or worse, multiple devices, the types of optimizations, and this is still like a fairly general purpose version, we haven't done any fancy tiling, vectorization, whatever else under the hood here to truly maximize performance, is going to differ a lot from device to device, let alone from the math at the very top that we wanted to start with. So to talk about, before we talk about how we can go ahead and fix this, let's talk about why the current systems don't fix this for us. So there's a wonderful utility inside of Julia called code type that will show you the sort of insides of how this gets compiled. And it turns out that the code type of our original code basically says, hey, you have your multiplication, you have your multiplication. Hey, we're going to go ahead and allocate now this sort of temporary variable here. We're going to go ahead and do our wonderful adds inside of this temporary variable, and then we're going to go and send it off. And one thing that you'll immediately notice here is these generic sort of pseudo runtime calls are very non-obvious what they're doing. To us, we know what they're doing because we knew it came from our high-level linear algebra, but to the Julia compiler, this is just some generic function call that could mean anything. It could touch all memory. Who knows what's happening under the hood? And it actually gets a little bit worse than that. If you just look inside of one of those map moles, this is a shortened version, because I wanted to at least pretend like it fit inside of a slide, of one of those multiplies. You see at the top we have all of these extra allocations. We have these type pieces. We have these comparisons. Eventually, we have this generic map mole, which like 3 steps down the compiler will eventually hit our wonderful gem utility, where we could have added that extra 2, like we talked about earlier. Suffice it to say, getting down to this level, or even from the top level down to that one place we could add that to, is really hard. So now I'm going to talk about this wonderful utility, or specifically compiler engine called MLAR. You've probably heard of LLVM. It's the default used inside Julia, as well as like Swift and basically every other language itself. MLAR, still part of the LLVM general ecosystem, but has a few key nice things. Specifically, unlike LLVM, where there's a predefined instruction set, which basically mirrors a C-like or sort of pseudo instruction level semantic, the definition of all of the MLAR instructions is completely up to the user. So, I or you or anyone else can define a new instruction that has whatever custom semantics that I want it to be. There's tons of these that already exist, some of which I actually helped develop, including those that say we have a built-in instruction just for linear algebra, just for GPU programming, for fully homomorphic encryption, and your imagination here can really go run it wild. It turns out the other really nice thing about MLAR is it lets you mix and match all of these different pieces together. So you could define a new dialect and combine it with my dialect, and we could do optimizations across these boundaries very effectively. It's so useful, especially the sort of linear algebra and the sort of accelerated programming sort of backends to MLAR, that nowadays all of the core infrastructure for machine learning, basically at every company, all goes through MLAR, be it JAX, PyTorch, TensorFlow, Triton, name your favorite sort of thing, it goes through MLAR to do codegen. And it turns out that there's plenty of really cool front ends that exist for MLAR, e.g. in C++, we've built a tool called Polygeist, and in this talk specifically, we're going to be talking about reactant. And a cool thing, just to give you like a little bit of a demonstration, I don't know if you've ever seen LLVM IR before, but it's very similar to that Julia IR, if not slightly even more verbose for those who have gotten some errors in the past. The MLAR version looks something like this. It actually appears to have a for loop. It has a store with some indexing off it. It looks fairly pretty. And the fact that it looks fairly pretty means that the compiler has that extra information to do nice things about it. So to give you some further intuition about why MLAR itself is useful, let's talk about GPU programming. And I'm going to be a bad person here and talk about GPU programming in CUDA and C++ before we get to inside of Julia. So one particular problem that GPU programming has is that those existing compilers, be it LLVM IR or even the Julia compiler, the recent work like Taper tries to fix this, doesn't have a good representation of parallelism. So here we have sort of a vector normalization. So we call this normalized function. Inside of the normalized kernel itself, we call this extra sum here. But it turns out, if we're summing over that input and we're only storing into that output, the value of that sum is not going to change per kernel iteration. So we're doing a ton of extra work every single kernel. In fact, we're doing O of n work for the entire kernel to be able to do that. Something that I'd really love to do is to be able to move that sum, hypothetically speaking, outside of the kernel to be done once, saving all the work across everybody. But even if it were possible to do that as an optimization, which even LLVM for regular CPU code cannot do, the GPU makes this incredibly hard. Specifically, you have two modules, one for the host code, e.g. all the calling context around it, and one for the device code. And these two pieces can't see each other, which means that in practice, not only can you not sort of move some code here all the way over to this area, it also means that you don't even know how many threads you're being called with, or if these things don't alias, or any other sort of passes that would enable some nice host device crossing optimizations. We built this wonderful compiler called Polygeist. It works in C++, but it also does a ton of optimizations for generic GPU and synchronizations. And effectively, if we compile this into MLAR, Polygeist style, we have a nice parallel for loop representing the GPU as follows. This enables us to do exactly that optimization like I talked about earlier. We could hypothetically move it outside of the loop. We could reschedule our kernels, figure out what the optimal shared memory size, block size, all those other sort of wonderful things. Do kernel fusion, host device optimization, tons of really nice things, including taking our GPU code and transforming it to go ahead and run on the CPU. And one thing that I'll say that we'll come back to in a second here is all these optimizations that we're doing on our original code from many enzyme papers that we've done in the past demonstrate the fact that if you do more optimizations on your code before running autodiff, you have a much, much faster derivative code as a consequence. Another sort of set of reasons why MLIR could be useful for us here in Julia. So we went ahead a little while back and we wrote a bunch of linear algebra optimizations for effectively a linear algebra dialect inside of MLIR. So here we have like a generalized dot product, right? A map mul, we have an element-wise multiply and an element-wise add. We wrote 200 plus of these, linear algebra simplifications. Some of these are easy, like, x plus 0 just goes to x. Some of these, are a little bit more tricky, like, transpose of x is itself, or transpose of map mul is swapping the input orders, and tons more complex things as well. To give you an intuition, again, for why this is useful, here we have our little simple code that has, 100,000 sized input tensor that we do some dot products and other stuff to. But it turns out at the end of the day, we only want the first 10 elements, which means we're doing all of this extra work here because we're only going to see those first 10 elements. So if we're going to just go ahead and add up 100,000 things and only slice off the first 10, it's way better if we could just slice off the first 10. So we do that. We push the slice up. And now that our B here, which multiplies 10,000 or 100,000 things together, is only using the first 10, once again, we can apply the same optimization and only do the first 10 elements from those pieces, and so on and so forth, and really propagate across your entire program the sort of linear algebra, mathematical, and other properties. And we built this inside of MLAR, which, like I mentioned, is used inside of all the big ML frameworks. And just for fun, we applied this inside of JAX in a state-of-the-art neural network training like the Gemma equivalent. This isn't the sort of version of Gemma / Gemini that's run in production, but a version of this sort of standard machine learning model that Google runs for all of the big things. And on a 32 TPU accelerator case, we got a 53% speed up in training by applying all of these linear algebra optimizations over standard JAX because of the need for both that linear algebra and then the combination of that with the automatic differentiation. For a single accelerator, we still get a fairly reasonable 14 to 18.5% speed up, which, considering that it's many people's jobs at Google to keep these machine learning models running as fast as possible on the hardware that they themselves build, being able to apply a couple of transpose rules is a fairly significant win. And if you're more curious about some of the logistics here and how we did this, there's a paper that we published at last CTO also introducing the transform dialect. So that's all very fun. But let's get back to Julia. This is JuliaCon, after all, right? So with that as a premise is why MLIR and a lot of these other cool things like user-defined optimizations are particularly cool, we built Reactant. Effectively, what this is, it is an optimizing compiler framework for Julia built on top of MLIR. So we can directly preserve all of that high-level mathematical and other semantics directly into the compiler. And this gives us a lot of really interesting benefits that I'll talk about. We can now optimize programs just like we saw earlier, doing all those fancy linear algebra pieces. We can also effectively retarget programs. You can write the program once with whatever sort of form of linear algebra that you want for your one node system. And we will automatically figure out how to retarget it, one, to your favorite accelerator, be it CPU, GPU, TPU, GraphCore, whatever else that you like, including distributed clusters of that, inserting all the communication commands for it. We leverage something called XLA, which is the state-of-the-art sort of parallel runtime used inside of all of these big ML frameworks, giving us, when combined with our optimizations, substantial, speed ups. And we're workable with fairly general purpose Julia code. We support mutation, we support control flow. I'll talk more about that in a second. Autodiff, all the likes, and this is all open source, of course. So to talk a little bit about what reactant is, or specifically how to use it, there are 3 important things that you need to know. So first, we have this concept of a reactant concrete array. We have a compile command, and we have a reactant traced array. I'll talk about more of these in detail in a second. A simple way that you would go ahead and use reactant is shown here on the left. Of course, we go ahead and we import our wonderful package. We have this conversion, reactant to our array, which will take a generic Julia data structure and then sort of convert all of the inner arrays to be reactant-owned memory. The reason why this is important is obviously if we're going to go ahead and run this on a machine or distributed set of machines, this lets us define an array that could be accessible on any piece of memory, including, again, sharded across multiple devices. We have our standard Julia function that we want to go ahead and use, and we have this wonderful compile command. What this compile command does is, given the function you want to execute, and then the various inputs, it will perform partial evaluation of all the non-reactant sort of inputs, effectively getting rid of type instabilities, getting rid of garbage collection. We'll see a little bit more about what that is in a second, and having a wonderful compiled version of our code here that now we can execute incredibly quickly for any arbitrary input. And of course, we go ahead and actually execute it. So talking a little bit more about that conversion, like I mentioned a second ago, we have some nice helper utilities here, reactant to our array, that'll take an arbitrary Julia struct and recursively go through and convert all the pieces. We see, in fact, even when we initially load reactant and do it, the machine that I was running on happened to have a GPU, so as a consequence, we're using GPU memory for this. No extra modifications required. We see here that the result of our execution here is a concrete or reactant array, and of course, like I mentioned, reactant found that there were 2 5090s, so it decided that's what it was going to use, both for the execution as well as the storage. And you can change this. It figures out by default what the best things are on your system. Second piece is compilation. Now, this is a little bit long. I'm not going to run you guys through this, but this is what reactant initially sees by tracing through and compiling the Julia code. So effectively, all of the underlying pieces, there was a broadcast somewhere inside of it, there was a conversion, there was all these wonderful things. But one thing that you don't see here is you see no garbage collection calls, you see no type instabilities, you in fact see the type for literally every one of these pieces, which is relatively nice. The other thing that I'll say is this is obviously before optimization, because we have a nice little flag there at code HLO optimize equals false. So we can optimize it. We can run through those 200 plus linear algebra optimizations and the like, and we get this code here at the very, very top, which is a .general, aka mapmul, transpose, and add. And in fact, we did the common sub-expression elimination for us, so we didn't do any of the extra pieces. The second piece here sort of represents the sort of direct runtime that we're actually going to go ahead and do. And if we look very closely at it, right here, specifically. This is just a single call to Kubla's dgem, meaning that we successfully turned this original code with all those sort of fancy things into a single mapmul call with no extra pieces inside of it, which is, again, pretty fantastic. The last piece that I'm going to talk about are these sort of traced arrays, like I mentioned. So reactant has 2 types of arrays, like we talked about a second ago. Those concrete arrays, which is where you go ahead and store your data. It can represent data stored across multiple machines or whatever else that you want to do. It's where you have all the pieces, similar to your coup array or whatever else. A traced array is slightly different. This is the array type inside of the compile command itself. The reason why is this represents data that is not a compile time constant, and effectively represents values that we're sort of generating all the code for, but we don't necessarily have those values at this moment for you to be able to use. So if I had this show here to the original command, we now see that our x inside of here, whereas x outside of the compile was a concrete array, our x inside of here is now a traced array. We can see both the pros and the cons of this approach. Like I talked about earlier, the pro of this approach means that, we've gotten rid of all of our type instabilities, we've partially evaluated all these wonderful things inside of it, but like I mentioned, you don't have the values of those pieces of data inside the code when you're compiling it. So here I go ahead and make a reactant traced number. The default is to trace all the arrays and not the numbers. If you want to trace the numbers, we have an extra flag like this. And we have a condition based upon this compile unknown value. And we try to go ahead, and by the way, we have a nice little syntax here at JIT, which just runs compile and then execute the compile. You usually don't want to do this because compilation will take a while, but for just doing a simple little test like this, wonderful macro. And we get an error that there's a non-Boolean, specifically this traced Boolean, used in a Boolean context. And that's effectively because at the time of picking which one of those two branches to go down, we don't actually have the value. So we need to figure that out. Now, reactant is actually a lot more general than JAX and these other sort of tracing-based tools, specifically because we actually get all the Julia IR. So we can see all of the original control flow, and we can convert that and preserve that into control flow in the MLAR. Right now, this is not done automatically, though we have some students working with us automatically doing this upgrade for us. But effectively, if you want that control flow to actually preserve both branches of it, we have a cute little macro here at trace that you can apply to an if statement, a while, a for loop, a function call, whatever else, and it'll compile a version where you have both of those branches available. And of course, we can go ahead and now run it. Like I mentioned a little bit earlier, reactant is wonderful in the sense that it lets you write your regular Julia-style code, and it'll automatically distribute it across whatever your favorite type of accelerator it is. Under the hood, this works by effectively reactant recognizing all the devices that you have available, or more specifically, what nodes inside of a cluster you might have, though of course it works equally well on my laptop as it does on a fancy cluster of these pieces. And then when it takes that tensor, e.g. the mapmol like we saw earlier, and it sees that there's only two devices, it says, okay, I'm going to do a partial mapmol on each one of these devices, and I'm going to send data across that boundary to be able to effectively compute the entire mapmol at once. And this is nice because now the user doesn't need to care about what type of system that they're running on, let alone how many things that they want to run on. We, the compiler, will now go ahead and do our best to automatically figure out how to place these pieces. Notably, a compiler is not magic. We do a good job. We run all these fancy optimizations that can be very, very difficult for a person to do in practice, like we saw a second ago. But this doesn't mean that someone couldn't sort of expert hand tune something a bit better. But that means we can write a new optimization that takes that into account, of course. And again, the big takeaway here is you can take your existing single node code, and you don't need to modify it to go retarget all of your favorite different systems. And fun example, we now have Julia on Colab with TPUs, default with reactant installed inside of it. You can go ahead and even run it on your favorite 8x TPUs or whatever else. In that case, eight particular devices. To give a brief sort of highlight of how important these types of optimizations are in practice. So we took the Lux framework here, and we compared running it with the default backend with CUDA.jl. Right, which unfortunately has to make all those additional allocations and cannot fuse together. You have this mapmol with a bias add after it into one kernel and the likes. And we compare that with reactant, where we can compile all these things together. We can get rid of those unnecessary allocations. We can fuse kernels together. We can use the super optimized cuDNN by recognizing that this is there. And overall, for various sort of model sizes here, we get between a 5 and a 15x speed up across both the forward time and the backwards, e.g. training time. And if you like this graph, hear more about it in the next section that Avik's going to talk about. A couple of other sort of really interesting things. So scientific codes, as an example, is the state-of-the-art code, oceananigans.jl, has hundreds of handwritten kernels. So whereas, in the first part of the talk, I spoke a lot more on hey, we have these existing linear algebra pieces, a lot of existing Julia code equally applies, is written with, custom kernels and the likes, which obviously those existing ML frameworks don't like, not to say that we're an ML framework or a general purpose compiler, of course. But really interestingly, if you look at the ways that the actual ML hardware, e.g. a TPU, was built, it was originally built when convolutional neural networks were a thing. So actually, TPUs are just giant convolution machines. And we happen to put a bunch of things that look kind of convolution or mapmol-like onto it. But if you squint at the type of stencil kernel, which is standard, in this case, inside of Oceananigans and even more general purpose code, it actually looks remarkably similar to a convolution. And yet we don't have any of these existing scientific pieces of code being able to run and leverage the big ML hardware. So another goal of reactant is saying, can we automatically take the high-level math and other structure that exists in the scientific world and now apply all of the sort of machine learning, both computing manpower and software engineering manpower to it. I won't go terribly deep into all of the details here, but effectively, we have a system based off of Polygeist earlier, integrated into reactant, that takes your existing CUDA code, we identify effectively the underlying tensor operations inside of it, So first, we find that we have our original Julia code. It becomes the LLVMIR code here. We convert it into those nice sort of affine parallel loops from what that generic CUDA kernel represented. It turns out that we can take our general purpose affine loops and turn them into sort of tensor operations. And finally, we can optimize it into a gigantic convolution, which is, again, exactly what we want to go ahead and run. And we actually took the state-of-the-art Oceananigans code, which has like 277 plus CUDA kernels, and we compiled the single node version of that CUDA code to run on thousands of distributed accelerators, including, I think it's 2,000 of the now second latest, because there's a new TPU that came out in between, TPUs from Google, as well as several thousand on regular NVIDIA GPUs. One more sort of cute in-progress work that I'll say. I mentioned earlier, of course, that Reactant is compatible with Enzyme, though, again, completely separate project. You can use Reactant without any fancy autodiff stuff. But it turns out that running all those optimizations before differentiation is incredibly crucial. That's what makes Enzyme fast in Julia via LLVM right now. All those extra linear algebra optimizations are also extra optimizations we want to run and combine with. So we took this con network, which I can't really tell you what it is, but it's a fancy neural network. We ran it the forward pass in regular Julia with and without reactant. And we have the backwards pass in this case with Zygote with and without reactant, and Enzyme on the inside, in this case specifically Enzyme MLIR. So I won't force you to do means because means are hard. But overall here, the original code, compiling it with reactant, you get a 2.14x speed up. On the backwards pass, that speed up on the primal results in a 13.5x speed up on the actual derivative itself. And again, pretty pictures are fun. So the actual version of the big code that we saw earlier results in some wonderful things like that. So again, overall, Reactant is an optimizing compiler framework for Julia, built on top of MLER. It lets you preserve all of those original high-level semantics, including discovering that from existing CUDA kernels and the likes. This lets you optimize programs to run faster and also retarget your programs to run on whatever sets of machines that you like. We work on top of XLA. Again, that's state-of-the-art runtime. That's used by all the big ML frameworks. So we are competitive, if not usually faster, than a lot of those big ML frameworks because we have our nice optimizations built in by default. And like I mentioned earlier, we're compatible with most Julia code. We have mutation, we have control flow, we have autodiff. And again, this is all open source. Thank you so much.
Thanks. Hey, excellent talk. Thank you. It looks like we're bypassing CUDA.jl with your package. Is that correct?
No, we are actually using CUDA.jl. So specifically, CUDA.jl is what's used to generate the LLVM code from the original kernels. We're then taking that LLVM code, and then we're converting it into the higher level form. So we're not using CUDA.jl for execution. We're using it for code generation.
OK, that's really interesting. Thank you. Could you talk about how, if there's any kind of control flow or anything like that that would not be, any Julia code that would not be compatible with Reactant?
Yeah, so like I mentioned, we want to compile this into a effectively super type stable version of the pieces. So the caveat is either you have to pick control flow where you pick one of the two branches at the moment. So if I go back to this slide right here, right at the top, where if that was a compile time constant in the sense that it was not a reactant bool, but just a regular bool, it would pick one of those two pieces. That's totally fine. Or the second approach, like I have down here, where this could be a non-compile time constant, and it'll emit both of these branches. This second case right here requires that the outputs be of the same type, basically because we need to preserve type stability across our compiled code. So there are some caveats here, but effectively you can have completely type unstable code out the wazoo at the top, but your control flow is limited in terms of the sort of conditional branches that you can make. Or you can have fully general conditional branches if your result types are the same.
Great talk. You mentioned you turn off the GC. Can you go more into that?
Yeah, so it's not necessarily that we turn off the GC, but within the Reactant compiled code here, we effectively make a single executable that runs through all of the internal multiplies, adds, whatever else out there was kernel calls, etc. Which means inside of here, there is no garbage collection call. because we've compiled, not necessarily a single kernel. We can decide based off of fusion heuristics to make multiple kernels based off of the application or whatever else. But as a consequence, within the call to the reactant function, there is no garbage collection because we've perfectly managed that ourselves on the inside.
Thank you. So this works for dense arrays, I guess. But what about sparse arrays, for example, sparse matrices or sparse vectors?
Yeah, so sparse arrays are partially supported in the sense that, if it can be built out of arrays and regular sparse arrays are built out of arrays, because that's a Julia primitive, we can convert it inside of here. That doesn't mean that you'll necessarily got the optimal sparse sort of matrix performance. That said, if we go look back at this sort of piece right here, right, where it's like, hey, you only extract out this one piece like you might do in a sparse array, actually our compiler optimizations, even if you didn't mark it as a sparse array but only happened to use part of it, will give you a lot of that same benefit as sparse arrays by default. The caveat here is this needs to be a structural sparsity as opposed to a data-dependent sparsity. So it just happens to be that a lot of these things are zeros. We won't currently optimize with that taken into account. If it's because you only read certain elements, we will take that into account. Adding native sort of sparse arrays, importing is something we're working on, though.
Is there, I guess, if so, then more a long-term path to get part of this into the Julia compiler?
Yes, so there's a lot of things sort of ongoing at the moment, which range from sort of like Julia compiler plugins, custom abstract interpretation and the likes. We see this as sufficiently useful that, starting to work and play on this, especially all the optimization stuff that is going to be independent of whether or not it's a package or the native Julia compiler right now. I know the core Julia devs have been looking a lot at how to enable sort of custom compiler passes. Effectively, all this is a custom compiler pass inside of a custom abstract interpreter. Currently, Julia base doesn't support you being able to do special things with that on the inside, but as that sort of eases up, we can migrate more and more of this into base. What, sorry?
The third simplification might have a problem there.
In what sense? Did I write a bug on the slide or just?
Yeah, it's the missing transposes.
Oh, yeah. Fair enough.
One quick question.
Yeah.
So you mentioned use CUDA-JL to extract the LLVM, and then you could optimize that with Reactant Framework. So can I pass, like let's say I extract I have my own custom library and I extract LLVM out of it, use it, and can I just pass it to your framework and you could optimize the CUDA-JL LLVM?
So the answer is yes. Ironically, we currently do something kind of similar for that from C++ because we don't have all this nice infrastructure like in Julia we can inject these pieces into. The caveat, right, is like we did a nice job setting this up to automatically hook in with CUDA.jl as the LLVM emitter and then, Razor inside of Reactant. So you might need to do a little bit more setup on your side to take your LLVM and hook it in, but all of the sort of transformation passes that we have here are general. You can start with LLVM and do whatever you like.
I feel like I'm missing something basic. It seems to me that you'd have a lot more information if you went from Julia to the raising step without compiling through LLVM. So clearly, I just am missing. Why would you lose all that information in the nice high-level language?
So the answer is we don't. If you come from existing, like matmuls or whatever else, from the base Julia operations, we will directly preserve that as saying like, hey, you wrote a matrix multiply inside of Julia. This becomes a matrix multiply directly from, in this case, the unoptimized code that we see. The caveat, right, is not all Julia code is based on top of high-level linear algebra optimizations or array operations, even though you can turn it into a bunch of individual slices. A lot of times people do write custom CUDA kernels, and we equally need to be able to support those custom CUDA kernels. So the majority of time that you use Reactant, assuming you're not calling into CUDA kernels themselves, it does directly preserve that high-level Julia semantics, but also it enables us to equally take low-level pieces that you've hand-scheduled or optimized or for any number of reasons chosen to write yourself, and we can still import and use that. Also, I apologize. I think we need to get to Avik's talk since we're now 5 minutes into his talk. Happy to take more of these questions offline.
So hi, everyone. I'm Avik. So I'm a PhD student in the Julia lab. And yes, I used to be working on this framework called Lux. And then, so this is going to be mostly a talk about like what's the state of deep learning in Julia. But it's mostly a talk about how we are using reactant to accelerate deep learning. So it's pretty much an extension, but with a more focused domain. So for people who are not familiar with Lux, so it's a deep learning framework that we built in Julia. And the main focus for that used to be for scientific machine learning workloads. So we had this like smaller neural networks embedded inside scientific simulations, and we needed them to be really fast, mostly on CPUs, but also sometimes on GPUs. So that used to be what the focus was. And yeah, I will skip over this slide because Billy did a great job explaining what reactant does. For some background, there used to be this package called diffq flux, which had this exactly 2 layers called fast chain and fast dense. And that is what like created the like baseline from which we took the design. And we essentially extended it for every single like deep learning workflow that you can think of. And today it's already being used in like the broader scientific machine learning community. So pretty much every single neural network framework that you come across in SciML is using Lux under the hood. Even like the modeling toolkit, if you're using neural networks via that, it's, again, using Lux. But this also kind of brings us into a problem. We kind of went into this hole where we are very nice on like CPUs and these kind of architectures, but when we try to scale it up on like GPUs, or there was no way on running on TPUs, we are kind of like very far behind a lot of these Python frameworks. So before going into like what we have been doing, I just want to give like a quick overview of how you would interact with Lux. And it's pretty much similar to how you do it with like Keras and all those frameworks. You first like define this, like in a DSL, you define the model. Then you say, oh, I want to select a device. So here you'll see, I'm saying, oh, give me a reactant device, which is exactly what reactant will do. It'll take like, oh, does this computer have a TPU attached to it? Then I will use a TPU. If it has a GPU, I'll use the best GPU available. And then you just transfer all of the data, all of your parameter states into the device memory. And then you just run, like Billy showed before. So you just do like add JIT call before your model call, and it will compute, it will do the forward pass. If you wrap it around with enzyme, it will give you the gradients. Now, so what are we kind of building out in Lux at this point? And it's mostly like we are kind of more deeply integrating ourselves with reactant, and also it enables us to hook into the broader XLA ecosystem. So all of the performance benefits that you see in Python, we not only get them, we also improve those performance by hooking into enzyme JAX and reactant. So as I mentioned, like we were really good at CPU kind of workflows, but let's see the current state of like the GPUs. So this is the benchmark that we ran. So this is relatively a simple model. So this is ResNet 50. So you can assume like those workloads are extremely heavily optimized, should have been optimized already. But if you look at the performance, you'll see that, oh, it's like we are 15x faster if you just swap out the CUDA backend with reactant. And it also, like, if you look at the right-hand side corner, it even, the memory usage for, if you use CUDA or like the Julia GPU backends, it's just so drastically high that it doesn't even fit into memory. And even when it sometimes fits into memory, the GC overhead is so extreme that it's just impossible to train these models. And the other nice thing is we're actually pretty competitive with JAX, right? So JAX would be like, these are heavily optimized, and we can just match the performance by just switching a backend. And just to showcase like how simple it is to migrate these things, so let's take like an old example of how you would train a Lux model. So you basically select your device, you specify the model, the parameters, data loader, and you just say, OK, I want to use Zygote, and I want to train with like the mean squared error. And now you just shift to this. And there's exactly 3 lines of code change. You switch out, you do not load CUDA, cuDNN, you load reactant. You switch your device, you just say, I want to use a reactant device. and you say, I want to use enzyme, because none of, like, at least at this point, none of the other AD backends will work with reactant. We are going to fix it soon, but yeah. And the other cool thing, so Billy mentioned about GC, so we do not have a lot of GC, like we don't have any GC overhead, so memory allocations and everything is super fast. The other nice thing is if you have like, let's say a chained broadcast, Julia will typically launch like 3 different kernels here. But if you go to XLA, it will actually just fuse up this whole kernel into, fuse up all the function calls into a single kernel on launch. And so, like, you first of all lose out, like, improve upon the kernel launch overheads, and actually and it also like lets you do very, very complex fusions. For example, let's say you have a convolution call followed by an activation function. Typically, the vendors ship out libraries which have like a special version which fuses the convolution with the activation. So we are able, like, if you look at the IR, we are able to do all those fancy fusions. I will just show us. This is like not a simple example. I don't really want you to look into what's going on here, but just to give an example, so I think there was like 6 or 7 different operations, and if you would have like used the base Julia, you would be like, okay, now let's launch 6 different kernels in sequence, and that would be terrible for performance. But if you use the XLA compiler, and this is only for GPU, you'll see all of those actually just got fused into this one massive kernel. And it happens all the time, and it's actually very critical for any kind of like machine learning performance. And we not only get this for GPUs, the same thing happens for TPUs as well. Now back to the slides. Yeah, so that was just to show that, yeah, it's not just for very simple use cases. You actually, fusions happen all the time. We have known that in the Julia deep learning ecosystem for several years now, that without fusions, we are not going to get the performance, and now it's actually possible to do those. Now, what else does reactant give us? It finally lets us do distributed training, and not just on like 4 GPUs that is present on my university cluster. I can actually run it on like thousands of GPUs and TPUs. And again, without changing too much of my code. Actually, let me pull up the Colab notebook here I have. I'll just share, like, give a rough overview of the code and then move on to the Colab. But here, this is pretty much the same pipeline that I showed you from earlier, right? You have the model, you move the model to devices, and you just call add_JIT. What is changing here is you're just saying, OK, we are just going to create 2 devices now. So the first one is how I'm going to divide up my data. I'll go into the details for this in a moment, but it's basically saying, OK, I want my device, like the data to be sharded in a specific manner. I want my parameters to be sharded in a different specific manner. And I just want to call compile on it. So you do not have to do any kind of manual MPI, all gather, or whatever you want to do. Reactant and Lux will automatically handle this for you. So let's just look it up in Colab. Yeah. So here I'm just pretending I have 8 CPUs on this Colab notebook. I'm just faking it because I do not have like multi-GPU on this. And so reactant is saying, OK, you have 8 CPUs. That's great. The first thing that I need to do is I need to say, OK, you need to divide up the data. So think of the devices as like a logical mesh, right? So here we have 8 devices. And what I'm saying is, OK, split it up into a 2x4 grid. Call it the x-axis, y-axis. Then you just define your function as like basically a addition of 3 tensors. Then you just say, OK, I have this x, which is like an 8x8 matrix. And now I want to split up the data. So what this essentially means is you're saying that, OK, along the x-axis, I want it to be divided across 4 devices, and along the y-axis, I want it to be divided across 2 devices. So every single device has only a particular chunk of data. However, when you're writing your code, you do not need to care about that. You assume that every single process has all the data it needs. And the compiler will figure out how to move the data such that you minimize communication, maximize performance, and yeah. So all the information here basically you provided is in this one line. You're saying that, OK, I want to shard the data, like the inputs, the 8x8 matrix, into this particular format that I mentioned with the name sharding. And then the compiler basically goes ahead and be like, OK, how do I rearrange the intermediate operations such that the sharding, such that I know where the intermediate operations are? And then you just run the code, and you see, oh, the final data is also now sharded. So this code was actually run on 8 devices, not just a single device. And yeah, it does something smarter than just saying, OK, let's all gather to everyone, and sorry, all to everyone, and just add. It doesn't do that. It does something very smart. And the same principle pretty much works for any kind of deep learning framework. So let's say, as an example, let's take batch parallelism. So the idea behind batch parallelism is you have like a single model, but you have like loads and loads of data coming in, right? So the way you would, the most naive way to train this kind of models would be, OK, I will split up my data across all the different devices that I have, do the forward pass, do the reverse pass, and then just average out the gradients at the very end before applying the optimizer, right? So it basically boils down to an all reduce at the very end. But again, we do not want to think about that, right? That's too much to think about. So what do? We just say, OK, we have 8 devices, construct a mesh out of it, move the parameters. So here, the parameters in this case have to be replicated, right? So all of the devices need to have a copy of the parameters. So we just say, oh, replicate it across all of the devices. For the data, split up the data across the batch dimension, and then just run the model. The code is just details, but overall, you can see you just specify how the inputs are divided across a mesh, and everything else is automatic. But in the previous case, you saw that, OK, we assume that every single GPU is really fast to be able to, fast and has a lot of memory to be able to process batches of data coming in. But we are moving to trillions of parameter regime right now, so it's not really a feasible thing to do. So now what we want to do is, OK, we'll still partition the data across devices, but we will also partition the models. So now you're in a more complicated regime, so it's not just an all reduce at the very end. Even intermediate operations need to have some kind of a communication. So now we are getting into the very fuzzy domain of how do you do it optimally, right? And it's pretty hard to reason about, and until date, we did not have any Julia solution to be able to do these kind of modeling. But again, with reactants, so here you just say, OK, instead of just putting the data on all the 8 devices, we create a grid now. So it's a 4x2 grid. 4 of the batches are assigned for, 4 of the, one axis is assigned for the data, and one axis for partitioning the model. So here, let's say you have let's say you have a convolution network, so the weights are like a 4-dimensional tensor. So here what I'm saying is, oh, for the first dimension, just partition the data on the devices along the first dimension. And for the data, partition all the data along the batch dimension, along the last dimension. Again, so you changed how the initial data partitioning is done, and you just run your code, and yeah, it just works. Yeah, so it is basically, if you look at from the previous slide, the only change I made was here there was reshape into an 8, and here it's reshape into a 4x2. So everything internally becomes automatic, enables us to scale, no MPI needed, and it's very generic. You do not have that many devices, just say sharding equals nothing. It will work on your single device machine as well. So we finally now have distributed model and batch parallelism inbuilt into Julia, enabled by reactant. And one of the other cool things that happened with this more of like an MLIR migration is it now lets us tap into the broader like C++ Python ecosystem of like tooling. Previously, we completely lacked tooling for introspection into this machine learning models. We always had profiling tools, but they're kind of hard to use. They have like, you need to set them up properly. They're not tailored towards deep learning. Whereas like if you look at PyTorch or JAX, like they have this fantastic tools which just gives you so much more information when you look at them. With an MLIR migration, we actually can just say, oh, give me the traces, and you can use TensorBoard, Perfetto, XProf. I'll just pull something up. So this fusion, for example, is what XProf is giving us. So I can look at the trace, and I'm like, oh, this operation looks really slow. What's going on here? So I can be like, OK, let me just click into this. It will take some time. But it will, yeah. So it will basically give you this graph. And if you want, like, oh, what are, not op stats, but yeah. I want to know which kernels were launched, how much, like, what is their bottleneck? Is that an HBM-bound kernel? Is that a compute-bound kernel? How can I improve the kernel? All kinds of miscellaneous statistics. And also, the exact same workflow now works for not just, so you just say reactant with profiler, and it will profile for your GPU, for TPU. You do not need to spawn up like a different kind of profiling tool for every single platform you're on. You just do one line of code. You get all of the aggregated information that is needed to accelerate these workflows. And this was a requested feature for quite some time, is how do you actually visualize these kind of models nicely? Yeah, you can look at this graph. It's not pretty, but that's not a solution. So what you could do, you could actually just dump the MLIR into this very nice tool called Model Explorer. And it'll actually show you in details, like, oh, this is the overarching structure of my model. So these are nice quality of life features that are like enabled by moving to like a MLIR backend. And finally, we have support for deployment. So you can take your trained model, you can export it to a saved model, and now you can go use any of your favorite TensorFlow tools. So you can be like, oh, I want to do it on an edge device. So you just take the model and just run it on an edge device. It just works. Java, you want to put it into JavaScript libraries. Again, that works. And it's pretty much a single line of code. So the PS and SD, that thing we are talking about, you just pass it into the serialization framework that we have inside Lux, and it just saves it. To be clear, there's also equivalent serialization version in Reactant, so even if you're not using Lux, and you have like a more general function than a neural network, you can still export it to saved model. And finally, to conclude, like, what kind of features that are we working on next on the Reactant and on the Lux side? So we are going to fully migrate out of the whole 80 nightmare situation that we have for machine learning right now. We are going to make Reactant the complete default. So anytime you call zygote.gradient, what will happen is we'll just sneakily compile Reactant and be like, yeah, here's the gradient for you. No more, like, we might keep Mooncake around. Some people want it, so let's see what happens there. But to get to that point, what do we need from Reactant? One thing is we need dynamic shapes. For example, when I showed you, like, you can just export the Lux model into TensorFlow, one restriction there is the batch size that you're using is going to be fixed, which is a problem because in production, you do not know what your batch size of the data is going to be, right? So you need that to be dynamic. So dynamic shape support we need in the Reactant front end. We already have those things in the back end, so it's not a big deal. You just need to find the time to do it. We need to figure out how to do custom rules. And we also need like a no-copy Julia array to XLA array. The reason for this is, let's see, if you're calling zygote.gradient with a Julia array, and if we just spend so much time copying the Julia array to an XLA array, people will just be angry at me. So the solution there is if we there are again APIs for this. There's something called DLPack, which is widely used in the machine learning ecosystem to basically let different array backends talk to each other. So we will not be copying over the Julia array. So the XLA array, which is the concrete R array, which Billy was talking about, it will just share the memory with the Julia array. So those things become really fast. And the other thing which has gotten really good is like we need to, because when we use it, let's say with Zygote, we'll be like, oh, add jitting, because we don't really have a mechanism of compiling the function and recalling it. So if someone really wants to use it with Zygote, we really need it to be like add jit needs to be really fast. Rather, add compile needs to be really fast. This is more of like the Lux specific thing. People really hate the custom layer interface that we have. We are going to get it removed, like not removed, we are going to keep it around, but it's going to become very simple. You do not have any state parameter management. It's going to be all automatically done from after like a couple of months. And finally, something that I really want to finish working on is for people who are familiar with Triton or Palace kind of thing. So these kind of take your array, like it's like writing a kernel, but you still use like a lot of array operations. So you kind of generate the MLIR from there and then like do the scheduling and lower it down to PTX. We do not have any kind of front end for it. And while you, we do have the excellent CUDA.jl kind of thing, but it's really hard to write low-level kernels. So it's like people in machine learning love using Triton and Palace because you can preserve, like you can use array operations at the high level. So I'm kind of looking at something like that. So we just expose it via React, and we can then write a lot of these fancy kernels directly in Julia, and it will get scheduled similar to how Triton works. And hopefully would also work with like Mosaic and TPUs. Yeah, and so that was the talk. If you have any questions.
So that ties a bit back also to earlier. Sometimes you have like the question, can we use semantic information of high-level constructs, and reactant can for the things it knows.
Yes.
But if I have my own high-level things and I know something, can there be something like reactant rules?
I can, yeah. Yes, it is possible to do that. And I think we at one point discussed like a custom front-end thing where users are able to say that, okay, this is my front-end high-level information that you should be preserving, and here are a bunch of, let's say, optimization rules for your custom front-end. Yes, so something like that is definitely in the plans, and I think MLIR definitely has like support for that. We just need to write up some infrastructure on the front-end, yeah.
Great talk, Avik. Thank you for all the work that you do and so for Billy. So in my, I guess, opinion, and I'll be selfish and only consider my workflows, there are two things that would hold me back from using Julia over PyTorch would be mixed precision training and something like flash attention.
Yes.
So what do you think are the bottlenecks? Like what would convince me and people like me to go back to Julia, which I would love to?
By flash attention, actually Triton's flash attention is really good. And one of my reasons why I want to do this kind of Triton-like auto scheduling instead of writing CUDA kernels is I want to enable exactly those kind of workflows that, okay, I want to be able to write flash attention and have the compiler figure out the dirty bits, right? So yes, we are working on that. And I would say the other cool thing, if you do write like a Triton-like thing, we can automatically differentiate that. So you do not need to be like, oh, here is the forward pass for Triton, and here is the backward pass for Triton. And then you register it with PyTorch. Enzyme MLIR allows us to differentiate pretty much every single dialect in existence, right?
So how would I pass Triton code to Julia? Would it be, like, can I just give it vanilla Triton code, or will I have to go through kernel abstractions or something?
So vanilla Triton, there is a way to pass in vanilla Triton code. It's a bit messy, so you need to compile the PDX, dump it into a Kubin file, call it from CUDA. Again, not the recommended approach. But for this particular API, Here we are going to be like, we'll expose like a Triton-like front end in Reactant, which you can see is pretty much like, actually, I can't see this. Yeah, you'll see like it has like the program ID constructs and it has like load and store pointers. It's very similar to that. So yeah, you will have to do some kind of a migration. Kernel abstractions, unfortunately, is extremely low level for doing like a Triton. Like, maybe I haven't thought about it too much, but I just think like the kernel abstraction, what's it called, the primitives for kernel abstractions, those might not work out for Triton. Again, we could do something fancy like the CUDA stuff Billy talked about and raise it back up and reschedule via Triton, like raise up a CUDA kernel. But then again, you come back to the problem of it's actually very hard to write CUDA kernels, right? Yeah, but to answer your question more directly, you will have to, like, if you want to migrate, you'll have to write out. Or there's another easier hack. You take the MLIR dump from Triton and slap it into Reactant. That works.
Hi, thank you very much. It was a great talk and amazing work. I was wondering, is there any limitation beyond the usual machine learning layers and models? Is there any limitation on the SciML part? Like, can you use any kind of differential equation or custom Julia code there? And then would that be compatible with Reactant and also for deployment with TensorFlow?
One thing that we need, so if you add like the add trace like on the for loops and the if conditions inside SciML, that is something we are exploring right now. So if you do it that way, it will work. But ideally, if you want to like integrate it with like the broader SciML ecosystem, you kind of would require that the if conditions and stuff get automatically like upgraded into a stable HLO if, which again we are working on. So it's mostly like a matter of, do we want that manual effort right now to inject those add trace everywhere? But yeah, there is no other kind of limitation directly to working. Yeah.
Well, thanks.
So Reactant is not a lightweight dependency, to put it very politely, and it cannot be. But if we want people to put things like trace in their code without having everything duplicated, can we have a super lightweight package?
That's an excellent question. And it's called Reactant Core. It has 0 dependencies.
Any final question?
When can Reactant be well integrated into SciML?
Okay, so for the packages in SciML that are only focused on neural networks, most of them have already been migrated to Reactant. Neural PDE, we have a summer student working on migrating it to Reactant.
That's physics-informed neural networks?
Correct.
Okay.
Yeah. Oh, I completely forgot to mention, you can actually do nested automatic differentiation thanks to enzyme MLIR.
Amazing.
Yeah. So we are doing that migration now. Coming back to like, there are other ones like deep equilibrium networks and stuff. We do need like custom rules for that because we know better analytical expressions and we know that differentiating the for loop is not going to work out. I would say give it a year for like the core, like a lot of the high-level machine learning packages to migrate, and a year after that for the more differential equation things to
Awesome.
work.
Thank you.
If there's no other questions, let's have a round of applause for both of our symposium speakers.
first talk that we have is for graph neural networks. So we have Aurora, who's going to be talking about this. She's a third-year PhD student in computer science at University
Côte d'Azur.
Côte d'Azur, sorry about that. Working on machine learning and graph theory, with a focus on temporal graphs and graph neural networks. She is also the maintainer of the open source package graph neural networks.jl, and she has previously contributed to this package as a Google Summer of Code and Julia Summer of Code student.
Thank you very much. So hello everyone, I'm Aurora Rossi, and today I will talk about the package graph neural network.jl. So let me introduce myself. So I am a third-year PhD student at University Côte d'Azur, and as Avik said, I participated to 2 Summer of Code, working on the library, in particular on the temporal graph aspect, and with the Google Summer of Code and Julia Summer of Code. And in October, I will start a postdoc at the University of Bonn. So. The content of today's talk are an introduction to the library. I will describe you the basic graph data structure we support. I will show you the message passing procedure. I will tell you the definition of graph neural network, some convolution that we have in the library, and how to create a new custom convolution. Then I will show you an example of a simple training code, and the graph dataset we can import from the ML dataset.jl package. Then I will describe the future plans of the package that we have for the package, and I will show a simple notebook about the Karate Club example. So let's start with the package. So it's an open source Julia multi-package that is designed to create and build, train graph neural networks. It was created by Carlo Lucibello and is inspired by Python geometrics, for example. And we recently published a paper on Journal of Machine Learning Research describing this package. And so I say that is a multi-package. In fact, it contains 4 main packages. So the first one is graph neural network.jl that contains the stateful graph convolution. So it's based on the framework flux.jl. Then we have GenN-Lux.jl that contains the stateless graph neural networks, and it's based on the Lux.jl framework. And then we have, so these 2 packages are meant for user. Instead, the other 2 are built-in function. So we have GenN-Lib.jl that contains the implementation of basic message passing function and the functional implementation of graph convolutional layers. And then we have GenN-Graph.jl that contains the graph data structure and the helper function. And this package depends mainly on graph.jl. And so you can see the 4 main dependencies that are Flux, Lux, graph.jl, and nnlib.jl. So now we move on with the graph data structures. So I want to recall you what is a graph. So a graph is a data structure where V is the set of nodes and E is the set of edges, where the edges are pair of nodes. And in machine learning, we can add some additional information at the level of the nodes, at the level of the edges, and at the level of the whole graph. And this additional information are called features, and usually are represented, for example, by arrays. And there are several ways to create a graph in our library, and the standard type is the GenN graph, which are always represented as directed graph. And here we can, for example, create a random graph with 10 nodes and 60 edges. Then we can add the feature at the level of the node, edge, and at the level of the graph. And you can see that the first dimension is the dimension of the feature, and the second dimension is the dimension, so the number of nodes, edge, and the number of graphs. So, for example, here we have just one graph. And here is the summary of the structure. Then we can create a graph starting from the adjacency matrix, for example, or the adjacency list in this way. And the last representation from which we can create a GNN graph is the CO representation. So we have two arrays that contains the source node of the edges and the target nodes. So for example, the first entry of source means that we are looking at the edge from 1 to 2, and the source node of this edge is 1. And then we have the target that is 2, because this edge goes in this way. And so this is another way to create a GNN graph. Then we support also heterogeneous graph, which are graphs with different types of node and relationship and edges. And for example, an example of a heterogeneous graph is a graph in which we have users and movies, and a user can like and dislike movies. And so you can create a GNN heterograph in this way, where you can define which are the relations, so the node from which they start, the kind of relation, and the movie. So, and the other node. And then here we give the edges as a CO representation. And then you also can manipulate this kind of structure. For example, you can add edges, and in this way you can add an edge that goes from node 2 to node 1. And also in this case, you can add data feature. And for example, if you want to add data feature at the level of node user, for example, you can add the age, and so you can do it in this way. Or you can do for the movie, and you can add the information about the release year. And again, here there is the summary of the graph, GNN heterograph. For the temporal graph, so temporal graph can model different situations in which we take in account the temporality, the time, and we can divide temporal graph in two cases. The first one is static temporal graph, that are graph in which the graph structure is fixed. So the topology is fixed while the feature change over time. And in this case, we can implement this using the GNN graph type that I described to you before. And after, we can also create a dynamic temporal graph, which means that both the graph topology and the feature change over time. In this case, we handle just the case in which the number of nodes are fixed and the edges instead can change over time. And in this case, the temporal graph can be seen as a collection of static graph, and so it is called a temporal snapshot GNN graph type. And also, in this case, we can create some snapshots. So, two, for example, a static graph. And then we can create a temporal graph and add the feature and also a label for the whole temporal graph. And here there is the summary of the graph. And then you can also access to the node data directly from the temporal graph. Now we pass to the message passing concept. So for those of you that are not familiar with the graph neural network, I will describe briefly the message passing procedure and the graph neural network definition. So the message passing is a procedure that can be divided in 3 steps. The first one is the computation of a message from the neighbor of a node. Then there is the aggregation of all these messages and the update of the current feature of the node. So in order to understand better these passages, let's look at it from the point of view of node 3. And so node 3 has 2 neighbors, and we can compute the messages from them. So we can compute 2 messages with a message function. And after that, with a permutation invariant function, we can aggregate the 2 messages. And after that, we obtain an aggregated message that we use to update the current information of node 3 with another function that is called update function. And this procedure is done in parallel for every node. We implement the message passing procedure using the propagate function, and it is divided in other two subfunctions that relies on the gather and scatter function that I will describe in a minute. But first, let's see the propagate function. So we can give to it the message function. So in this case, we just add +1 to every message. And then the aggregation function is the sum. And so we obtain for each node, the value is basically the double of the degree of the node in this simple case. And let's see how to create this using gather and scatter. So this is a very simple graph in which we have as a feature some scalar, 5, 6, 7, and 8. And so we can create the messages using gather, and the first input vector are the feature of the node, and then the second are the source of our co-representation. And then we create our message function as before. I just put +1 for simplicity. We apply the message to every message that we collected, and then the updated messages can be produced with the scatter function that takes the messages, and then they are mapped to these indices, so this destination that are the target of the co-representation. And so, for example, 6 in the first that is the first message will go in node 3, and so we will see it here. And then we repeat the procedure, so the second message will go to the first node, and as the 7 and 8, so we obtain 21 because we have the sum function that put together with the sum all the messages that go in the same node. And then we have 9, that is the last one, that go in the node 1, so we see it here. And there are no information that go to node 2, and so it's 0. Okay, so now we are ready to define what is a graph neural network. So a graph neural network is the message passing procedure in which the update and the message function are learnable function, and in this case are neural networks. And as every machine learning architecture that can be trained, in the case of supervising training, you have to it is an optimization problem in which you have to minimize a loss function, but probably all of you are familiar with this concept. And so what are the tasks that GNN can perform? There are several tasks, but we can group them in 3 main classes. So the first one is the graph classification, link prediction, and node classification. So graph classification is the problem of determining the category of the graph. So after performing some message passing layer, we have some updated feature that we want to group together. So we sum all of them together with the pooling operation, and we obtain only one array that is called graph embedding. And this is the input of a multi-layer perceptron that will classify our graph. Similarly, we can do the node classification, so we want to determine the category of a node. We perform some message passing layer, and after that, we want to understand the category, for example, of node 6. So we take his feature, we use it as the input of multi-layer perceptron, and again, it will give us the class of the node. And the link prediction, instead, is the problem of determining whether there will be an edge between two nodes. So after performing some message passing layer, we can choose two nodes that we want to understand if they will be connected or not. So as before, we give the feature as input of a multi-layer perceptron that will give the answer yes or no. Okay, so in our library, we have a list of graph convolution that are already implemented. So you can, and we support, for example, the graph isomorphism convolution or the graph attention convolution, some of the most famous convolution. But of course, you can also customize, create your own graph convolution. And to do that, you have to create a struct in which you put all the weight and parameters of your convolution, of your layer. And then you create a constructor in which you initialize the parameters and the weight. And after that, you have to create the forward function that will apply the graph convolution. And you can create layers, but you also can create model. So, for example, here you can create a model that has two convolution and a dense, so a classifier. As before, you create the constructor and then the forward pass. In this case, the example is with Flux, but similarly, you can create it in the Lux ecosystem. So here, there is a training example in which we create some synthetic data. We create the training set. We create a model using GNN chain that work similarly to the chain of Flux and Lux. So it is useful when you don't have to customize your model. You just use the chain with already built-in function and layers. Then you define the optimizer, the loss function, and then the training loop is very simple, very similar to the Flux and Lux ecosystem. We support the dataset that are contained in ML dataset.jl. There are all these graph dataset. So we support static, temporal, and heterogeneous dataset. Some of them are collection of dataset, like the TU dataset and the OBG dataset. So, future plan. We would like to optimize the message passing operation and improve the sparse metric operation on GPUs. And actually, this is a work in progress by Davide Ferré as a project of the Google Summer of Code this year. Then we would like to support additional hardware backends, such as the Apple Silicon Metal and TPUs. Because now we are supporting CUDA and AMD GPU. And we would like to also enabling multi-GPU training. So now we can move to a very simple example of the Karate Club network. So this is the QR that brings you to the notebook. And so if you click on the link, this is the notebook. So the Karate Club graph is a small graph that contains 34 nodes, and each node represents a person in the Karate Club. And we want to, so the dataset can be imported from the MLL dataset.jl package, and the task we want to perform is to classify the cluster of people that meet outside the Karate Club. And so we can find in the dataset the graph, but also the feature that are the label of the club. That is label for each person of the club and for each group outside the club. So the first person will go out with the people of group 1 and so on. Okay, so we can import the graph using this function that creates the GNN graph. And then, given the fact that in this case we have just one graph, the training will be using just a subset of nodes, and we will test to the other part of the graph. And to do that, we need a training mask that select which node are used in the training set and which are not in the training set. And then we, of course, create the on-batch labels, and we have the GNN graph. Okay, and then this is the graph of the people in the karate club and the communities that are outside the karate. And instead, this is the simple model that we use that has 3 convolution and 1 classifier. Okay. And then we can visualize the embedding before the training, and we can see that already we can see the communities that are quite together. And then we use the logic cross entropy as lost. Then here, this is the training loop that I described before, and we can see that the loss function is decreasing. And then we have the, sorry, it's not, oh. We have that the training accuracy goes to 100, and the test accuracy is 80. And this is the final embedding. And we see that in this upper part are the blue nodes, and then on the other side there are the yellow node, the purple node, and the green node. Okay, and with that, I would like to thank you for your attention.
Thanks for the talk. So yesterday there was a talk by, I think it was yesterday, by James Fairbanks about AC sets. And in that talk, he talked about how a lot of graphs that have metadata can actually be represented as like higher level graphs like hypergraphs or multigraphs or other kinds of combinatorial data structures. And it looks like graph neural networks use a lot of graphs with metadata. So do you think any of those sorts of techniques would make sense to be applied to graph neural networks?
I'm not familiar with that kind of structure, but probably yes, there should be already some model that work with simple or complexes, something like that. Yeah.
Thanks. That's impressive. I'm curious. You mentioned that there's some famous packages that have been supported, like Sage, like graph attention networks. Where I assume simplified, just very simple graph convolution networks. I guess from a developer perspective, do you have a sense of what additional package, what additional model choices that you want to focus on next?
I focused on the temporal models. In fact, here there was not the list on the temporal part, but yeah, probably we would like to focus on the models that are the most used one and the newest one. So yeah,
cool. Thanks.
Thank you.
Thank you very much for your presentation. I learned a lot. So I'm not from the field, but I'm wondering, like, how do you compare your implementation against, what I could find in Python? Like, what would be really the selling point of your work against, what exists outside? So.
we did in Julia because was missing a package about graph neural network that was maintained because there is a geometric flux, but we think that is a while that is not anymore maintained. And so yeah, it's just mainly for the Julia user. And we think that also we have a lot of features that are missing with respect to the Python geometric library because there are less people that are working on the Julia library. And we still have to do a benchmark, but we think that the performance should be the same because we are working on GPUs, so yeah.
But maybe like in terms of, how, because somehow you have a domain-specific language to say what actually you want to do. So maybe this is where, it could be interesting to compare as well, not just in terms of performance, but also like how do you express a workload, how do you express some work, just an idea.
Okay. Thank you.
Hey, thank you so much for the talk. I had a couple questions. I was really impressed early on, also in the presentation, with regards to kind of the plethora of, I guess, graph neural network specific types that you had for different types of graphs. You were mentioning like these temporal graph structures, things like that. I was just kind of curious, is there any interest in the work that you're pursuing to perhaps spin some of those types out into its own package? I'm just wondering, because some of my work would be really interested just using some of those structures, like temporal graph structures, monitoring that over time, tracking feature changes as time evolves. I was just very curious if you're thinking about keeping that consolidated within kind of the stack that you're presenting at the very beginning, or if you're thinking about maybe spinning it out into other, like maybe graphs compatible, like graphs.jl compatible packages, or what are you thinking?
Yeah, at the moment we are keeping everything in that package. We recently split the package in graph neural network and GNN lags just to handle the true machine learning ecosystem. But yeah, at the moment we are keeping this format. Yeah.
Okay. Thank you so much.
Thank you. Yeah, and one thing that I didn't mention before is that with respect to Python geometric, for the temporal graph part, we are at the same level, basically, yeah. Because there is the Python geometric temporal package, but that one seems not to be maintained, and they are trying to put in Python geometric the temporal graph, but I'm not sure if they are at the same level of us. Yeah.
No, this just seemed very advanced. That's why I was wondering. Okay.
Thank you.
I have one question. You mentioned that you're looking at supporting reactant for like different hardware backends. Have you done any experiments with that? And if you have, like, are there any shortcomings that you have faced?
No, I am not aware of the details about that. Yeah. Thank you.
Okay, if there are no more questions, let's thank the speaker once more.
Thank you.
Yeah.
As well, but there's a HDMI right at the back that should directly there.
Might want to set that down.
Yeah, sorry.
Okay, so for the next talk, we have Jeremy presenting Evo trees, efficient boosted trees for CPUs and GPUs in Julia. Jeremy is the head of science at EvoVest. He's responsible for the development of systematic investment strategies in global equities. He has also worked previously as a research scientist at Element AI and as a consultant at WTW. So, Jeremy.
Thanks. Hi, everyone. Is the sound acceptable? Great. Thanks for coming to this talk about Evo trees. So I'm going to talk about somewhat old stuff, as Evo trees is a project that was initiated in 2019. But upside, I think it speaks that it's a package that has been kept up and going and has been useful in the ecosystem, particularly as gradient boosted trees are a bit of the workhorse in machine learning in the tabular data space. So I'm going to go over a bit what's going on about gradient boosted trees, present a bit what are the key aspects of the algorithm, also discuss a bit of the latest features that were introduced in the package, discuss some work more specifically around custom losses that are not following the usual gradient pattern, as well as discuss the future development for the library. So just to start, how is a problem setting that will typically be a good use case for the algorithm? We're having a table, in this case, a good old data frame. One of the variable is our target. Here it's the Titanic data set. So the survive is the target we'll look to predict. And we have a bunch of feature names, different columns. Something to note here is that the types of those features are not strictly numerics. Where Evo trees has been designed such as to be more of a table-first algorithm, so it has a first-class support for Booleans and categorical variables. Essentially, the treatment comes in two flavors, whether the variable is ordered, so that concerns all the numerics and ordered categorical variables, or unordered, which is the unordered categoricals, for example, if we're having a feature such as colors. So that will be handled directly by the algorithm and will allow to dodge some feature engineering, for example, one-hot encoding that result in a sparse representation of 0 and 1s in multiple columns. Rather than doing that, we can simply encode an integer that will be treated in a different way as a one versus the other, which will be more efficient in terms of memory. Now, Evo trees follows the MLJ interface approach. So we implement the same logic of the fit and predict method. So what we need to do is two steps to train a model. We first need to define its container for the upper parameters. So that's the config that we have created here with the Evo tree regressor. And a key element to specify is the loss, here the log loss. Here we're essentially doing a logistic regression. If you're into vanilla regression, it will be the mean square error you'll be interested in. Note that there are multiple other losses that are supported. In terms of regressor, we have like support for Tweedy and gamma distributions, as well as quantile regression. We have a Evo tree count that fits a Poisson distribution, and as well as Evo tree MLE for maximum likelihood estimators that supports probabilistic distributions. So for example, for the Gaussian distribution, we can get, instead of a single scalar prediction by observation, we get both the mu and sigma estimators for this probabilistic distribution. Now that we have the config, we're ready to fit. That's the usual method. There are some flavors different to the vanilla approach of MLJ, which is meant to support as a first class the out-of-sample evaluation. When it comes to iterative models, whether it's deep learning or gradient boosted trees, we want to track the metrics on an out-of-sample data set. This algorithm can overfit, and it will overfit on your data. So just throwing vanilla configuration for the model probably will result in disappointing results. So the idea is to pass data eval, so the D eval that you've seen here. And this will going to track your evaluation metrics by default. And with the early stopping rounds that is specified in the config, we'll get this kind of trace that will be interrupted at 99. And this will represent our best rounds. And now we have a model that we know has been stopped at an appropriate training level. just to illustrate the logic of boosted algorithms rely on a collection of weak learners. In this case, we have 4 weak learners. The first one might look like an unhealthy tree. It's a single rectangle, but actually the first tree is used to set the bias. It's oddly enough something that wasn't done, for example, in XGBoost until their V1 release, but it's a good practice to start with a proper base level when learning our trees. So we see that the logic of boosting is essentially the same as stacking algorithm. It's just that we successively learn kind of simple weak models that we will learn the residual over what has been learned by all the underlying weak learners. So you see how the prediction evolves into a pretty good fit for the data that we have at hand here. I'd like to talk a bit about the special tricks that make gradient-boosted trees particularly efficient. It's not necessarily the gradient part, but all the efficient implementation like XGBoost, LightGBM, and CatBoost, as well as Evo trees, rely on the same kind of representation, which is histogram. So the idea is to have a quantization of all of our features. And to do that, as a result, we get the model perspective on our feature is the view that we have at the bottom. So instead of having this continuous set of variables, all the model can see are those 8 bins. This is also an illustration of how gradient-boosted trees algorithm are invariant to the feature scale and distribution. Now a little bit more about the logic and how we can gain parallelism benefits from the histogram method. Essentially, the objects that we're dealing with when we build our histograms is first the IDs of the observation that belong to each of our node. And from those node IDs, we're able to fetch within our data that's being represented as quantized information. So that the data bin ID is essentially a matrix that contains the number of observations times the features. And this matrix is efficiently stored as a unsigned integer 8. So that explains why the number of bins is limited to 255, which typically is plenty enough even to capture the linear effects. So we have to fetch the ID for each feature. And now we get the gradient for the node ID, and then we can accumulate this into our histogram. So in the end, when we perform the operation to identify the best split candidate, all we need to operate over is a histogram that compresses our feature, our number of observations into a limited number of bin IDs. We can see that this kind of histogram building lends itself well to parallelization. So on CPU and GPU, we parallelize over the feature names. There's no issue there. But you can see that for the histogram on bin 1 in green, that sums to 6. Well, if we parallelize over observations, there will be collisions. So on CPU, we don't do any parallelization over observations, but we do on GPU. And that explains that we rely on atomic addition. This comes with an overhead, but the benefits from the parallelization is still better than ignoring this parallelization. Now, how do we fare against the other libraries out there? On the CPU, we're now at a pretty satisfying level. As you can see, if we have shallow trees, depth of around 6, we can reach speed up from 1.5 up to 2 times the speed of XGBoost. That's, I think, a good testament of the ability to develop algorithms, high-performance algorithms directly in Julia, while XGBoost is a very mature and well-optimized C++ library. On larger depth, though, we're pretty on par with XGBoost. That being said, there's still juice to be exploited on the Julia side, notably on the histogram computation. There are opportunities, for example, to represent the gradients as static vectors, and this gives us some further improvements on terms of speed. On the GPU, though, the story is less beautiful. We're quite lagging behind. I think for the smaller number of observations, it's not so much of a concern as a CPU do just as well, so there's no much reason to rely on those kind of accelerator. But definitely on the 1 million and more, we'd like to get on par, and I'll get back on that as we have a tangible steps taken to address this situation. Now, some latest development. We have tree bagging support. The idea was to be able to emulate the behavior of random forest. It's a kind of a classical algorithm people get introduced early when they learn about machine learning. The setup of stacking lends itself well for random forest. The only difference about random forest is that instead of learning residuals over what has been learned so far, each of the tree learn directly the target of interest. So the random forest is really just an average of the prediction of independent observations. So the support for tree bagging was quite trivial to implement. If I present here the high-level algorithms that happens in Evo trees, we can see that all we needed to update was a small loop to go over the bag size. So if you are interested in fitting a random forest, all you need to do is to specify a number of rounds of 1, have a bagging size over 8, and have a learning rate, or ETA, of 1, and then you'll get a random forest. But as a word of caution, note that and be reminded that we're dealing with weak learners, and for gradient boosted trees, we rely on an approximation of the loss function. So gradient stands for the fact that the loss function used in defining figuring out the best split relies on second order approximation. So if we're doing a regression, the loss function is a perfect match. So this is what we see, whether we look at the mean square error in green or the mean absolute error in blue. We have a pretty good model with n rounds of 1, so essentially a random forest. Whereas if we present this problem as one of logistic regression, now things turns out to be a little ugly, and this is not specific to Evo trees. I've had it in purple XGBoost, and it's just as bad. And the reason is that the second order approximation for the log loss is not that great, so we need this process of incremental learning that comes with stacking to get a proper fit. So word of caution about that. Another feature more recently introduced is the support for the oblivious tree structure. So this is a structure that is used in CatBoost that has been developed by the team at Yandex. So the difference is that for ordinary binary trees, the split condition is defined independently for each of the nodes. So we see here the 3 different colors. We start at the root node with the feature number 3 that is selected with its own split point. Same for each of the child. They all have their own split conditions. With the oblivious structure, it introduces more constraint on the structure. It imposes the condition that the split must be the same for all the nodes belonging to a given depth. So the root node will be the same whether we use a binary or oblivious tree, but as we go deeper on the tree now, it enforces a difference in the structure of the tree. In practice, though, I haven't seen much cases where this kind of regularization by structured resulted in important gains, but it's an option that might be relevant in certain kinds of noisy datasets. I'd like to discuss a little bit more, again, to introduce a bit the work that has been done about alternative approaches to losses. And here I'm illustrating further how this gradient approximation to loss behave. So we have a tree observation here represented as the three dark blue dots. And we see the residuals. So essentially, pretty simple situation, -6, -1, and 1. So we have a mean of 1. So what happens with the gradient estimation that is quite clever when it was introduced by XGBoost originally was that we only take the perspective that we are in our reference point is at 0. So what we look at is the first and the second order gradients at a prediction of 0, and based on that we can have this quadratic approximation that gives us the exact loss function for any prediction for each of our individual observations. And since we have this, those curves can be added and result in the same quadratic form, we can sum them and have now the green line, which represent the loss profile for the entire node that is being considered. And this is, once we have that, it's trivial analytical solutions to get what is the prediction that's going to result in the greatest reduction in the loss function. Now, what happens if we're interested in some other kind of loss functions, like mean absolute error? Well, that doesn't work so well if we add the individual loss functions. We'll get the first and the second order gradients for sure, but the second order gradient here is 0, and we can visually also intuitively understand that there's no analytical form or closed form analytical solution for those kind of loss curves. Yet there's something that was a bit bugging me when we were looking for those kind of alternative to loss functions, is that do we really need to have both the first and second order gradients if all we know is that the mean square error will lead us to select the mean of the leaf observations as the best move to do? And if we move towards the mean, then this kind of amplitude of the change in prediction could be kind of a good indicator of what is the gain. And this is what has been done with the actual mean absolute error, is that we're simply accumulating a single information per observation, which is the residual, target minus the prediction, instead of the first and two order gradients. And since those computations are the very heavy ones on the gradients and both the accumulation, we can save compute time and at the same time have a somewhat more robust estimator for in our vanilla regression. So here the mean absolute error can be confusing, as we're not literally fitting the mean absolute error at the observation level, but instead we're looking at the mean absolute error at the collective leaf level. Now, another approach we've taken as alternatives to gradient losses was to consider a situation that was a bit bugging us. When we look at a split candidate, here, let's say we're looking at a split candidate for bin number 3. So we have those observations in blue that are all bulked together, and then on the right side, all the green points bulked together. We can get a view that will have, for example, a gain of 250. And here, the blue and the green have a spread of 1, and there's a standard deviation of 1 within each of the leaf. Now, let's imagine a situation where those blue and green points would be much more much less distributed, much less dispersion in those observations. We get a situation where the mean is the same, -5 and 5 for each of the leaf candidates. Yet, when we look at the gain, it's still 250. But intuitively, if we look at those situations, it seems like it's not really, it should be like an arbitrary selection of those two conditions. We should prefer the one where there's less volatility, so we should go with the one in the lower right side. So how could we address this? The approach was inspired by the actuarial science credibility. This notion is essentially one of Bayesian approximation. So in technical terms, the credibility terms is that the best linear approximator for the posterior estimation of the mean. So the idea is to balance two sort of volatility. If there's a lot of if the variance of the hypothetical means is high, that means that there's large expected dispersion about the mean of different groups, so the different leaves altogether. So if there's a large expected discrepancies in the values of our leaves, that gives a stronger indicator or greater credibility to the observations coming out of this leaf. On the other hand, there's the expected value of the process variance, which is interested by the variability that happens within a given group. And so if there's a very high volatility within a group, like we see on the left side, then we should limit the credibility. So the idea was to have an estimator where we look at the mean, but shrink by a credibility factor. And to get those estimators, all we needed to do was to accumulate two informations, the first and the second moments of the distribution of the points, and we could derive the estimated variance by the simple relation that the variance being the expectation of the x squared minus the mean squared. So now if we look at the result, what we have now is on the case where we have a lot of volatility within the leaf candidates, we have a gain of 100, whereas with the situation where the volatility is much lower, now the gain jumps to 480, and now we've kind of solved this arbitrage problem about the confidence or trust that we can have about the prediction we're going to do in each of the leaf. I would note that this work was also inspired by some aspiration to have a automated way to tune the learning rate, the ETA. So the idea being that, well, if can we escape these arbitrary settings of the learning rate and have an objective measure based on the validity of the observations? Turns out, however, that this didn't converge well as we move to very close to the final stage and final convergence. The credibility falls near zero, and so we have a too early stopping mechanism if we rely on this credibility measure as a way to automatically tune the learning rate. Just to highlight the performance, the metrics, I think the key word here is essentially you can see that the metrics are quite equivalent on the regression problems that we've tried, comparing those alternatives to the vanilla mean square error. What remains to be tested, I would say, is on our real-world data sets here internally at EvoVest on our investment problem. So I cannot speak about how it performs in the real world while. Now, some words about what's coming up for the library. As I mentioned, we are having some performance gaps with XGBoost. We've taken an initiative with the CML Small Grant Program to improve that story, and it's quite positive. We just posted this earlier this week, and there's already someone that raised the hand. So we will already have someone working on improving the GPU performance. The objective is to bring it within 25% of XGBoost training speed. And as a bonus, we'd like to have the support for the histogram building through kernel abstractions in order to extend the support from CUDA device to AMD device as well. Another direction is for the multi-target support. The idea is to be able to specify a vector of targets and have the same tree structured directly predict a vector of predictions. So that can be also a way to enforce a regularization by structure by having a single model to perform multiple classification problems or regression problems. Finally, some exploration on AutoDiff has been initiated. The idea is to support user-defined losses. So for a mean square error or any kind of point estimation error, such a routine could work fairly easily. But the problem is that the benefit is, I think, not so much important if we have a single point definition of a loss function, like a mean square error or log loss. Implementing those within the library should be trivial, or if it's not, you can just raise an issue and this should be solved easily. I think the interesting use cases involve situations where the predictions, for example, we'd like to have, like in case of fairness in machine learning, we'd like to have our general prediction of the observations to be penalized, such as to remove potential correlations with a given restricted factor. So if we're doing rate making in insurance, perhaps you don't want to have a penalization over some protected groups, for example. And what if we could directly implement those kind of constraints in the tree structure? That could be done if we implement this at the loss level. However, with the default approach to gradient approximation, we need to have the second order approximation, which will result in an explosion of the parameters that would be essentially the square of our number of observations. So that this is kind of problematic if we want to enforce those kind of penalty. And so the work on that I just presented with the mean and absolute error, for example, was I think a first toe in exploring an approach where we only rely on first order gradients and be more inspired by the kind of learning steps like with deep learning solver, SGD or ADEM, and then be able to have a constrained number of parameters, yet being able to include effects and constraints coming from the global perspective of the whole predictions or the entire predictions within leaf levels, which at this time would not be, I think, a feasible approach given the second order dependency that we have in our losses. So that was what I have for today. So thank you for your attention. I'd be happy to take any questions.
Thanks a lot for your work on this package. It's a great package. Just a couple quick questions about the random forest thing. The settings that you mentioned, does that make it like 100% equivalent to a random forest, or is it just similar to a random forest?
Oh, to reinforce? I'm not familiar enough with the actual algorithm that they have to make a statement about the comparison, or maybe if you have further details, I'd be happy to...
Well, I mean, the settings that you showed where you set like the number of bags to 8 or more,
yeah,
and the learning rate to 1. As far as you know, is that pretty much equivalent to the standard random forest algorithm? Not necessarily what's in that random forest package, but...
Okay, I would have to dig about the specific of reinforce, but the logic is really totally respect the logic of the random forest approach. But as I mentioned, I think the main difference is that the trees in gradient boosted trees are not meant to be we're not designed to be self-sufficient trees that directly generate a great model by a single tree.
Right.
But at the same time, if it's a regression problem, so MSE error, I wouldn't see a reason for this approach to perform worse than the canonical random forest implementation. Okay. And just to note, I think the idea here was not necessarily to only allow the ability to do a random forest per se, but perhaps to save times on the gradient updates, so that you only perform once the gradient updates, then build a few trees, and then continue the iteration. So it's more about having a mixing mode of and compute saving, not as much as random forest, which right. I'd be surprised you'd get better result than going with the proper gradient boosted tree approach.
Okay, cool, thank you.
Welcome.
I have one question. So recently we have been seeing, especially with symbolic regression and stuff, that people are exposing Python versions of the Julia library. And since you presented that performance compared to XGBoost, at least for CPUs right now for mid and small size problems, is actually pretty good. Have you considered exposing a Python version, and ideally with a scikit-learn interface so that more people can use it?
Good question. I haven't considered it as originally, before coming to Julia, I was coming from the R ecosystem, and I first had a R binding. So originally, we trained our models through R pipelines calling Julia. yeah, I think it would make sense. It's just like those kind of work are motivated by the use case. So unless we have a tangible like use case, it's kind of hard to dedicate resources in that direction. But yeah, if anyone shows an interest, I think it could be interesting to expose that.
Awesome. Yeah. Okay, let's thank the speaker once more. Do we have Shiva in the room?
Any, sorry?
You need an adapter.
No, I have everything on me. Just the HDMI.
Yes.
I go here? Okay.
Yeah, I mean, if you show the video, just move it to the next slide. But yeah, I'm not sure how to do that.
Let me make sure we can see this on the screen. I'll give you the thumbs up on the screen.
But I can get 30 minutes nevertheless because I have a lot of material and demos, etc.
What?
I can get 30 minutes nevertheless because I have a lot of
Yeah, you can
demos,
get 30
etc.
minutes, yeah.
Okay.
So hi everyone. The next talk will be by Samuel. He will be talking on enhancing deterministic voice control with LLMs. Sam is a computational scientist. He's responsible for Julia Computing, Swiss National Supercomputing Center at ETH Zurich. So.
All right, thanks. Is the microphone good like that? Okay, perfect. Yeah, so welcome everyone to this talk about enhancing deterministic voice control with LLM interaction. Yeah, as I said, I'm Samuel Omlin. I work at CSCS, and now this is a private project which started out of necessity, and I believe ended up in something that can give a great performance boost to everyone. And I hope the demos will convince you of that. So the challenge that we want to solve, I guess, in the coming years is seamless integration of LLM intelligence into small everyday tasks on our desktop computer. And we want to save, I guess, everywhere a little bit time here and there, little task. Always use LLM to be a little bit faster everywhere. So you could think, okay, should I just talk with AI agents? They can do actions, right? But well, they're powerful, but the problem is hallucinations and ambiguity always in the input of the user. So it's not safe to give them unrestricted control over our PC. So we want to interact with LLMs for potentially everything, but keep full control over the actions. And so what I propose is that we just interact with the LLM, and but then we decide completely what actions we take. So we have deterministic voice control with LLM interaction. And now compared to the traditional text chat, like you know when you go on the website, ChatGPT, etc., this is much less cumbersome because you don't have to copy stuff inside, out again, etc. And nowadays there are powerful distilled models. For example, Dixie came along and many more. And they can be executed on commodity hardware, which opens new avenues. And important here when you run stuff locally is that data privacy is very simple, and we also get minimal latency. So that was the introduction. Then now I will quickly go over like the past talks at JuliaCon, which give the basis. And then, oh, sorry, this is kind of outdated. So, and in the end, do conclusions on future work. Sorry about that. The slide before was not the right one. Yeah, so previously, at the beginning, I made a talk, a fresh approach to open source voice assistant development. And I presented there the basics. Like you can, for example, create a weather forecast function like that. You say, how is the weather today or tomorrow, right? Just program it like that in one simple function. you pass the day as an argument, and you say with this voice args macro that this day should be taken as a voice argument and not as a normal argument. And then besides, we can write functions like that very easily. We can define a dictionary of commands, where on the left we have a command name of one word or a couple of words, which map then to a function or to a keyboard shortcut. And then afterwards, as a third step, we just pass this commands to just say it when you start it. Also, we had a per command choice between maximum speed or accuracy. Smart speech to text. We unite here Python and Julia. And so now I get to the second talk at JuliaCon. So this was a quick assembly of personalized voice assistants with Just Say It. So here I thought, okay, we need still something more. So you see there at the bottom, we can assemble a dictionary out of many dictionaries. And so like before, we still have functions in the dictionary that defines the commands. But now also we have commands, for example, VS Code or Firefox. And when this will be started, it will either be launched if necessary, or else just open the window opened if it's already open. And very important now, we can pass in a dictionary of arguments that are supposed to be started together with this application. So it creates a tree of of commands, and you will always have the commands you need. And furthermore, I introduced arrays in order to define sequences of actions. So you cannot just map to a single shortcut or a single function, but to a sequence of them and many other things. All right, so that was the quick review. Now the new approach in order to integrate LLMs. So we use the Python package Olama or the Julia package prompting tools to interact with LLM. And when we make a call to an LLM, we can automatically get the text, the content from the clipboard or the selection. And also I added, you see here this little symbol, added the TTS, so text-to-speech. So it means that in the end, the large language model can talk back to you. Now, so the approach here is we have, for the integration is we have automatic installation of everything, pulling, loading, and performance testing in a very simple way of the LLM, automatic configuration of prompting tools to use these models as well. Also, we can pass an API key to use a remote model. And the Just Say It functions, they can also directly handle prompting tools types. And then, so this is copied out of the terminal. So then in practice, if you have, for example, the Gemma model here, 1 billion, you get here about, on this notebook, 80 tokens per second, which is quite a good performance. And you see it runs 100% on the GPU here. Now for SST, we have a dual approach. So low latency constrained recognition with WASC for the commands, and a faster implementation of OpenAI's Whisper for the free speech, because there we need really something very accurate. Now I come to the demos. Unfortunately, they have a little artistic effect on the sound. because of the recording software, so the quality is not very good. So also the voice output is really like a human being. It's just now here it's a bit distorted. So it's time to say this. I will just increase the volume a bit. Okay, so I increase the volume a little bit and then continue. So the first demo is about the speech to text, and we use here sentence to say we want to start a sentence, or continuation to say we want to continue a sentence, and these other commands here, I also use them in this little demo.
We cannot hear it. So maybe you can bring microphone closer to your laptop or something, but we cannot hear it.
Okay, so sorry that you couldn't hear that. But you could see it, right? So it did put that to the maximum. Sorry.
If you can plug that into your headphone jack, then I can put it through the speaker.
So this was also not streamed now.
It will go through the stream.
But until now it was not. So should I repeat it?
Please.
Okay. Sentence. Good evening, Peter. Comma. Paragraph. Continuation. Here is the news about GPU-accelerated supercomputers from 2018 that I mentioned yesterday. Colon. Paragraph. Paste. Right, so you could see that you can mix talking, like saying a sentence with commands, like for example, paste, etc.
Excuse me, could you also replay the previous one?
We don't have so much time. Now the TTS demo here, to show how you can say read this, pause, resume, etc. Such as we read it. Internet. Triple. Read this.
New GPU-accelerated supercomputers change the balance of power on the top 500.
Triple. Read this.
For the first time in history, most of the flops added to the top 500 list came from GPUs instead of CPU.
Resume.
Is this the shape of things to come?
Triple. Internet.
Now, to define and program LLM interaction, we have, well, different submodules with predefined functions, which use voice arguments, etc. And in particular, we have this LLM module. And so with this, for example, we have all these functions available. And so when it says text in the function, this is that it takes the text from the selection or the clipboard. And so I will here demonstrate quickly the summarize, answer, and chat follow-up. So chat follow-up is really talking to a voice chat bot.
Triple. Summarize.
NVIDIA Tesla GPUs are contributing a significant portion of the extra flops in the top 500 rankings, primarily due to new supercomputers utilizing these GPUs.
Triple. Summarize. Triple. Answer. Which processors are most used?
NVIDIA Tesla GPUs.
Triple. Chat follow-up.
Listening.
What means flops? One sentence, please.
Flops refers to the number of floating point operations a computer can perform in 1 second, a measure of computational power.
What means supercomputers? One sentence, please.
Supercomputers are incredibly powerful computers designed to solve complex problems much faster than regular computers.
Bye.
Bye.
Chat follow.
Then we can also type the output instead of giving it back by voice. So I say type summary or type answer here. So here I'm selecting the whole text, the rest of the text, and then I'm copying into here. And I say type summary. And you see it types the whole summary. Now here I'm selecting the summary itself.
What is the take-home message?
So based on the summary now, it wrote the take-home message. So that was all the demos. Now, alternatively, instead of using these predefined functions, we can also use 7 functions here that allow to very quickly define like an anonymous function. So for example, here we have a voice chatbot defined like that. Listen is to make a speech to text. Ask is to ask the LLM for something, and say is in the end to say the result of the LLM output. Then, as I said, it's integrated with prompting tools, so you can also just use the AI macro here, AI string macro, and that would exactly do the same as the previous slide. Then, of course, alternatively, as I said before, you can use voice argument functions to do really the most complicated things. Now, one last important thing. We can really do application-specific definition of LLM interaction. So remember that one of the most powerful features of Just Say It is that command dictionaries can be defined per application. And so this allows us to get more efficient interaction with LLMs and better results than out. And so, for example, here, as an example, it took Jupyter, and so you could say, for example, generate magic, and tell it I want to do list all the variables that are uppercase or start with a certain letter, and it would automatically prefix this instruction in front of it, so it would know that what you want to do is to generate IPython magic. And we can also do it completely without voice arguments if you use these functions with the 2 here at the end. And then we have just predefined prompts that we can run that use the text input from the clipboard or selection. And we could even go one step further, for example, select a cell in Jupyter and say automatically create on top another cell, and then invoke afterwards this function in order to put the result, right, to explain the cell. But because typically you have a code and you want to explain it, so you want to create the cell on top and explain it there. Right, so I get to the conclusions and future work. So we really have a quite seamless integration of LLM intelligence into a small everyday task on PC, like that. We have application-specific commands to enable even more efficient LLM interaction. And we can have almost human-like interaction thanks to text-to-speech. And I think that bridges some gap in human-AI interaction that has not been done before. Now, future work is to release this presented version, because I could just finish all the features before the conference, but I still need to make the documentation and update the unit tests. But you can already check out the branch LLM and test it, and then define your own commands, hopefully, for your favorite application and share them on this repository. I myself, I will also add on this repository some productivity recipes, such that everyone can use like these LLM functions, etc. And
sleep, just say it.
Going to sleep. To awake me, just say awake, just say it.
Sleep, just.
All right, with that, I conclude.
Thanks. Very nice work, very interesting and fun. So all of these, the demos that you showed, were using Gemma 3, and also
yes.
Which other, the text-to-speech, speech-to-text, you were using also all open source version models for that?
Yes, so the model is the Gemma 3, like you said. Then the for text-to-speech, it's a Kokoro model, and speech-to-text, it's the faster Whisper implementation.
And also, you showed that you can define like predefine commands for each application. and you have to select which application you are using, or it already automatically detects what window you are or something, or how that works?
So when you start an application, say for example Firefox, then it will automatically load the commands that you pass there in the dictionary, in the command dictionary, together with the command Firefox. If you remember at the beginning, I showed that.
But you have to run the application through the same terminal or something like that, or?
No, you have to say Firefox,
okay.
And then it will load, start the window plus load the corresponding commands.
Thanks.
Or sorry, I said, that's another. I said internet, not Firefox in that case, yeah.
Thank you for the package. I've been playing around with it, and it seems really fun. I guess two questions I had. One is, if I understand correctly, you still have to have the dictionary to initiate the voice interaction, right? You can't just have it running sort of in a continuous fashion, or did that change with this version, that you can sort of have a continuous conversation? It looked like you were having the continuous conversation there.
So how it works, you create a command dictionary, which can be really big, what I'm using, and you give that to start, just say it. And then this will run in a loop, and you can say non-stop different commands, internet, then you go into internet or Slack, VS Code, etc. And if now you want to get to talk just to the LLM, then you would say chat or chat follow-up, for example, in this case, right?
Do you have to initiate each interaction with chat follow-up then? Or is it continuously listening once you're in chat follow-up mode?
Once you're in chat follow-up, it's listening until you say bye, yeah.
Oh, okay. Okay, so that's a wonderful improvement. I guess the other thing I was thinking about is, I'm not familiar with the Fast Whisper, but I was wondering, I noticed that you have the delay after you do the speech to text as it's processing everything. And I wonder if you've considered, for example, Apple's built-in speech to text does like a double pass where it does a low fidelity pass initially so that it can sort of output text as you're speaking, and then it does a secondary high fidelity pass, and it will overwrite any mistakes, if that's something possible, or?
Yes, that's absolutely possible. Actually, with the first version, with the WOSC, when it was purely WOSC, not yet Whisper, I tried that, but I found it confusing. It would non-stop write things that are not true and then change it again.
Right, yeah.
Because it was not so strong, right?
You have to kind of not watch
now
it
with the Whisper, I guess it could be strong enough that it wouldn't change all the time and would really be helpful, yeah.
Cool. Well, thank you.
Let's thank the speaker once more.
Yeah, the speaker is here now? No. Oh. Oh. Then I would have needed to go so fast. Then I would not have needed to go so fast. Okay. I could. You would like to hack a bit on that? Yeah, I would be happy to.
I dabbled with it quickly in my talk as well. I'm really interested in what we can do with that.
Okay, yeah. Yeah, I'd be happy to do something with you, yeah?
Yeah, that'd be awesome.
But so you need to type because I need the voice control.
Right, well that's the thing. I'm actually really glad the schedule changed because I was debating between this and Stefan, so I do want to go see his package. I'd love to talk to you more because I'm